Have you ever gazed up at the night sky and wondered how everything came to be? The universe, with its vastness and complexity, is a captivating subject that sparks curiosity in all of us. In this video, we'll embark on an exciting journey to explore the formation of the universe and our very own solar system, around 13.8 billion years ago. But how did our sun, planets, and moons come into existence? Through a process called accretion, tiny particles collided and fused together, forming larger bodies. Over time, these bodies evolved into the planets we know today, each with its own unique characteristics and mysteries. In this video, we'll delve deeper into these cosmic phenomena, unraveling the secrets of our universe and solar system. So, buckle up as we explore the wonders of space and prepare to have your mind blown by the incredible story of how everything around us came to be. The Big Bang Theory is the leading explanation for the origin of our universe, and it all begins with an initial singularity, a point of infinite density and temperature. Approximately 13.8 billion years ago, this singularity underwent a rapid expansion, marking the birth of space and time as we know it. In a fraction of a second, the universe ballooned from subatomic scales to the size of a grapefruit, a phenomenon known as cosmic inflation. This explosive growth set the stage for everything that followed. As the universe expanded, it began to cool, allowing fundamental particles like quarks and electrons to form. These particles eventually combined to create protons and neutrons, the building blocks of atomic nuclei. Within just a few minutes, the universe cooled enough for these protons and neutrons to fuse, forming the first light elements: hydrogen, helium, and trace amounts of lithium. This primordial nucleosynthesis laid the foundation for the stars and galaxies that would emerge later. One of the most significant pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, CMB. This faint glow, detected in every direction of the universe, is a remnant of the hot, dense state of the early universe. It provides a snapshot of the universe just 380,000 years after the Big Bang, offering crucial insights into its age, composition, and evolution. Understanding the Big Bang Theory not only helps us grasp the origins of our universe, but also deepens our appreciation for the cosmic tapestry that surrounds us. The formation of galaxies is a fascinating process that began shortly after the Big Bang, driven primarily by the forces of gravity and the presence of primordial gas and dark matter. As the universe expanded and cooled, regions of gas began to clump together due to gravitational attraction. Over time, these clumps grew denser, leading to the formation of the first stars and, eventually, galaxies. Gravity played a crucial role in this process, pulling matter together and allowing it to coalesce into larger structures. Galaxies come in various shapes and sizes, each with unique characteristics. The three main types are spiral galaxies, elliptical galaxies, and irregular galaxies. Spiral galaxies, like our Milky Way, feature a flat, rotating disk with arms that spiral outward, filled with stars, gas, and dust. Elliptical galaxies, on the other hand, have a more rounded shape and consist mostly of older stars with little gas or dust, making them less active in star formation. Irregular galaxies lack a defined shape and often result from gravitational interactions or collisions with other galaxies. As galaxies formed, they didn't exist in isolation. They began to group together, forming galaxy clusters, collections of hundreds to thousands of galaxies bound by gravity. These clusters can further combine to create superclusters, the largest known structures in the universe. Understanding the formation of galaxies and their interactions helps us piece together the grand narrative of cosmic evolution and our place within it. The process of star formation is a captivating journey that takes place within the vast regions of galaxies, primarily in areas known as nebulae. These nebulae are massive clouds of gas and dust, rich in hydrogen, helium, and other elements. The star formation process begins when a region within a nebula becomes dense enough for gravity to take hold, causing the gas and dust to collapse inward. This collapse leads to the formation of a protostar, a hot, dense core that continues to gather material from its surroundings. As the protostar evolves, it undergoes several stages, eventually reaching the main sequence phase, where it spends the majority of its life. During this stage, nuclear fusion ignites in the core, converting hydrogen into helium and releasing an immense amount of energy. This energy creates the outward pressure that balances the gravitational pull trying to collapse the star. The life cycle of a star is determined by its mass. Smaller stars, like our Sun, will eventually exhaust their hydrogen fuel and expand into red giants before shedding their outer layers and leaving behind a white dwarf. In contrast, massive stars undergo a more dramatic fate. After exhausting their nuclear fuel, they can explode in a supernova, a cataclysmic event that disperses elements into space. The remnants of these massive stars may collapse into neutron stars or even black holes, regions of space with gravitational pulls so strong that not even light can escape. Understanding stellar formation and evolution not only illuminates the life cycles of stars, but also reveals the intricate processes that shape our universe. The formation of our solar system is a remarkable tale that began around 4.6 billion years ago, from a rotating disk of gas and dust, known as a protoplanetary disk. This disk formed from the remnants of a massive molecular cloud, and as it collapsed under its own gravity, it began to spin. Within this swirling disk, particles collided and stuck together in a process called accretion, gradually forming larger bodies known as planetesimals. These planetesimals continued to collide and merge, eventually giving rise to the planets we know today. At the center of this protoplanetary disk, the Sun formed from the gravitational collapse of material. As the Sun ignited nuclear fusion, it emitted powerful solar winds that cleared away much of the remaining gas and dust in the inner solar system. This process played a crucial role in shaping the orbits of the newly formed planets, establishing a stable arrangement that we observe today. The solar system is characterized by two distinct types of planets: terrestrial and gas giants. Terrestrial planets, like Earth, Mars, Venus, and Mercury, are rocky and dense, formed closer to the Sun where temperatures were higher, allowing only solid materials to condense. In contrast, gas giants like Jupiter and Saturn formed farther out, where cooler temperatures allowed for the accumulation of lighter gases and ices. This differentiation in composition and location highlights the dynamic processes that govern the formation of our solar system, ultimately leading to the diverse planetary system we inhabit today. Our solar system is a fascinating collection of planets and their moons, each with unique characteristics that contribute to the diversity of our cosmic neighborhood. Starting with the inner planets, Mercury is known for its extreme temperatures and lack of atmosphere, while Venus boasts a thick, toxic atmosphere and surface temperatures hot enough to melt lead. Earth, our home, is unique for its liquid water and life, and Mars, with its red surface and polar ice caps, has long intrigued scientists searching for signs of past life. Moving to the outer planets, Jupiter is the largest planet in our solar system, famous for its great red spot and numerous moons, including the volcanic Io and icy Europa, which may harbor subsurface oceans. Saturn is renowned for its stunning rings and has a diverse array of moons, such as Titan, which has a thick atmosphere and lakes of liquid methane. Uranus and Neptune, the ice giants, have unique features like Uranus's tilted axis and Neptune's dynamic storms. In addition to our solar system, the discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary systems. Thousands of exoplanets have been identified, revealing a wide variety of sizes, compositions, and orbital patterns. Moons play a crucial role in understanding planetary systems, as they can influence their host planets' geology, atmospheres, and potential for life. Studying moons helps us unravel the complexities of planetary formation and evolution, providing insights into the broader mechanisms that govern celestial bodies in our universe. The universe is a stage for a variety of cosmic phenomena that captivate our imagination and challenge our understanding of physics. Among the most intriguing are black holes, neutron stars, and supernovae. Black holes form when massive stars collapse under their own gravity, creating regions of space where the gravitational pull is so strong that not even light can escape. Neutron stars, on the other hand, are the remnants of supernova explosions, incredibly dense objects composed mostly of neutrons, with a mass greater than that of the Sun compressed into a sphere just a few kilometers wide. Supernovae are spectacular explosions that occur at the end of a star's life cycle, releasing an enormous amount of energy and often outshining entire galaxies for a brief period. These cosmic events are crucial for the synthesis of heavy elements, which are scattered throughout the universe and eventually incorporated into new stars, planets, and even life itself. In addition to these phenomena, dark matter and dark energy play significant roles in the universe's structure and expansion. Dark matter, which does not emit light, makes up about 27% of the universe and influences the motion of galaxies and galaxy clusters. Dark energy, accounting for approximately 68% of the universe, is thought to drive its accelerated expansion. These cosmic events and phenomena are not just fascinating, they are fundamental to shaping the universe's evolution. By studying them, we gain insights into the laws of physics, the origins of matter, and the ultimate fate of the cosmos, deepening our understanding of the universe we inhabit. In this video, we've taken a fascinating journey through the formation of the universe and our solar system, uncovering the intricate processes that have shaped the cosmos. We began with the Big Bang theory, which explains how the universe emerged from an initial singularity and expanded, leading to the formation of fundamental particles and elements. We then explored how galaxies formed from primordial gas and dark matter, highlighting the role of gravity in creating these vast structures. As we delved into stellar formation, we learned about the stages of stellar evolution, from nebulae to main-sequence stars, and the significance of nuclear fusion in powering stars. We also discussed the unique characteristics of our solar system, including the differences between terrestrial and gas giant planets, and the importance of moons in understanding planetary systems. Finally, we touched on various cosmic phenomena, such as black holes, neutron stars, and supernovae, as well as the roles of dark matter and dark energy in shaping the universe. Now let's dive into how the Earth and ocean is formed. The story of our planet begins over 4.5 billion years ago, when dust and gas from the solar nebula coalesced to form the Earth. This tumultuous period was marked by intense volcanic activity and frequent collisions with other celestial bodies. As the planet cooled, water vapor released from volcanic eruptions began to condense, leading to the formation of our oceans. These vast bodies of water not only shaped the planet's surface, but also played a crucial role in creating the conditions necessary for life to emerge. Oceans are often referred to as the cradle of life, and for good reason. They provide a unique environment where complex chemical reactions can occur, leading to the formation of organic molecules. Understanding how life began in these primordial waters is essential for unraveling the mysteries of our existence. The oceans are not just a backdrop. They are a dynamic and ever-changing ecosystem that has influenced the evolution of life on Earth. As we dive deeper into this topic, it's important to appreciate the incredible diversity of ocean creatures that have evolved over millions of years. From the tiniest plankton to the majestic blue whale, the ocean is home to an astonishing array of life forms. Each species plays a vital role in maintaining the balance of marine ecosystems, and many have adapted in fascinating ways to survive in their unique environments. By exploring the origins of our oceans and the life they harbor, we gain insight into the interconnectedness of all living things. This journey not only enhances our understanding of biology and ecology, but also highlights the importance of preserving these vital ecosystems. So, join us as we uncover the captivating story of Earth's formation, the development of its oceans, and the emergence of life that continues to thrive beneath the waves. The formation of Earth is a remarkable tale that began around 4.5 billion years ago, rooted in the cosmic dust and gas that filled our early solar system. This primordial material, composed of hydrogen, helium, and heavier elements forged in the hearts of stars, began to coalesce under the force of gravity. As particles collided and stuck together, they formed larger bodies known as planetesimals. Over time, these planetesimals continued to collide and merge, gradually building up the mass that would become our planet. During this chaotic period, Earth experienced numerous collisions with other celestial bodies. These impacts were not just destructive. They played a crucial role in shaping the planet's structure and composition. For instance, one of the most significant events was the collision with a Mars-sized body, often referred to as Theia. This cataclysmic impact is believed to have led to the formation of the Moon and contributed to the tilt of Earth's axis, which has profound effects on our climate and seasons. As Earth continued to grow, it remained in a molten state due to the immense heat generated from these collisions, as well as the decay of radioactive elements within its core. This molten phase was critical for the differentiation of the planet's layers. Heavier elements, like iron and nickel, sank to form the core, while lighter materials rose to create the mantle and crust. Eventually, as the planet began to cool, a solid crust formed on the surface, allowing for the development of the first oceans. This cooling process was essential for creating a stable environment where life could eventually emerge. Understanding these formative processes not only sheds light on our planet's origins, but also helps us appreciate the dynamic nature of planetary formation in the universe. The formation of Earth's oceans is a fascinating chapter in our planet's history, intricately linked to volcanic activity and asteroid impacts. In the early days of Earth, volcanic eruptions were rampant, releasing vast amounts of water vapor, carbon dioxide, and other gases into the atmosphere. As the planet cooled, this water vapor began to condense and fall as rain, gradually filling the low-lying areas and creating the first water bodies. Additionally, asteroid impacts played a significant role in delivering water to Earth. Many of these celestial bodies contained ice, and when they collided with our planet, they released this frozen water, further contributing to the formation of oceans. Earth's atmosphere was also crucial in the development of oceans. The early atmosphere, rich in greenhouse gases, helped to trap heat, allowing temperatures to remain conducive for liquid water. As the atmosphere evolved, it became more stable, enabling the accumulation of water in the form of oceans. This process not only shaped the planet's surface, but also created a unique environment where life could eventually thrive. The significance of oceans extends far beyond their role as mere water bodies. They are vital in regulating Earth's climate by absorbing carbon dioxide and heat, which helps to moderate global temperatures. The oceans act as a buffer against climate extremes, influencing weather patterns and contributing to the water cycle. Moreover, oceans are home to diverse ecosystems that support an incredible variety of life forms. From the smallest plankton to the largest whales, marine life plays a crucial role in maintaining ecological balance. Oceans provide food, habitat, and breeding grounds for countless species, making them essential for biodiversity. In summary, the development of oceans was a pivotal moment in Earth's history, laying the foundation for life as we know it, and shaping the planet's climate and ecosystems. Understanding this process helps us appreciate the intricate connections between water, life, and the environment. How life began. The origin of life on Earth is one of the most intriguing questions in science, particularly regarding how it began in the planet's vast oceans. Two prominent theories that explore this mystery are the primordial soup theory and the hydrothermal vent hypothesis. The primordial soup theory suggests that life originated in a warm, shallow body of water rich in organic compounds. According to this theory, lightning and ultraviolet radiation provided the energy needed to trigger chemical reactions, leading to the formation of simple organic molecules. Over time, these molecules combined and evolved into more complex structures, eventually giving rise to the first living organisms. On the other hand, the hydrothermal vent hypothesis posits that life began in the deep ocean, near hydrothermal vents. These vents release superheated, mineral-rich water from the Earth's interior, creating a unique environment that could support life. The extreme conditions, including high temperatures and pressures, may have facilitated the formation of complex organic molecules. This theory highlights the potential for life to thrive in environments previously thought to be inhospitable. In both scenarios, simple organic molecules play a crucial role in the emergence of life. These molecules, such as amino acids and nucleotides, are the building blocks of proteins and nucleic acids, which are essential for cellular functions. The transition from simple to complex life forms is a gradual process, driven by natural selection and environmental pressures. Environmental conditions are vital for the emergence of life. Factors such as temperature, pH, and the availability of essential nutrients create a suitable habitat for chemical reactions to occur. The oceans provided a stable environment, protecting early life forms from harmful radiation and extreme temperatures found on land. In summary, the theories surrounding the origin of life in Earth's oceans offer fascinating insights into how simple organic molecules evolved into complex life forms. Understanding these processes not only sheds light on our own beginnings, but also informs the search for life beyond our planet. Diversity of ocean creatures. The oceans are home to an astonishing variety of life forms, showcasing a rich tapestry of biodiversity that ranges from the tiniest plankton to the largest whales. This vast array of organisms can be classified into several categories, including phytoplankton, zooplankton, fish, marine mammals, and invertebrates. Phytoplankton, the microscopic plants of the ocean, form the foundation of the marine food web, while zooplankton, which includes tiny animals and larvae, serve as a crucial food source for larger creatures. Fish, ranging from colorful reef dwellers to deep-sea giants, exhibit incredible diversity in size, shape, and behavior. Marine mammals, such as dolphins and whales, are known for their intelligence and complex social structures, while invertebrates, like jellyfish and octopuses, display unique adaptations that allow them to thrive in various marine environments. One of the most fascinating aspects of ocean life is the unique adaptations that many species have developed to survive in their specific habitats. For instance, the anglerfish has evolved a bioluminescent lure to attract prey in the dark depths of the ocean, while the octopus possesses remarkable camouflage abilities, allowing it to blend seamlessly into its surroundings. Similarly, the narwhal, often referred to as the unicorn of the sea, has a long spiral tusk that serves as a sensory organ, helping it navigate and find food in icy waters. The ecological roles of different ocean species are vital for maintaining the health of marine ecosystems. For example, coral reefs, often called the rainforests of the sea, provide habitat and shelter for countless marine organisms. Predators like sharks help regulate fish populations, ensuring a balanced ecosystem. Additionally, filter feeders, such as oysters and clams, play a crucial role in maintaining water quality by filtering out pollutants and excess nutrients. In summary, the diversity of ocean creatures is not only awe-inspiring, but also essential for the overall health of our planet. Understanding this variety helps us appreciate the intricate connections within marine ecosystems and the importance of conserving these vital habitats. How the first creatures on Earth came and went into extinction. Welcome to our exploration of one of the most fascinating chapters in Earth's history, the rise and fall of the first creatures that roamed our planet. Picture this. Over 3.5 billion years ago, life began in the form of simple microorganisms in the primordial oceans. These tiny beings, often invisible to the naked eye, laid the groundwork for the complex ecosystems we see today. They were the pioneers of life, adapting and evolving in ways that would eventually lead to the diverse array of species we know now. But with every rise comes a fall, and the story of these early creatures is also one of extinction. Throughout Earth's history, dramatic shifts in climate, catastrophic events, and even the gradual changes in the environment have led to the disappearance of countless species. The mystery of extinction is not just about loss. It's about understanding how these early life forms shaped the planet and influenced the course of evolution. As we delve deeper into this topic, we'll uncover the significance of these ancient organisms and their impact on Earth's history. From the first single-celled organisms to the complex life forms that followed, each played a crucial role in the development of our planet's biosphere. Join us as we unravel the enigma of how these remarkable creatures came to be and the factors that led to their extinction. Get ready for an engaging journey through time that highlights the delicate balance of life and the ever-present shadow of extinction. The origins of life. To understand how life first emerged on Earth, we must journey back to a time when our planet was a very different place. The primordial environment was characterized by intense volcanic activity, with molten lava and gases spewing from the Earth's crust. This chaotic landscape was accompanied by vast oceans, rich in minerals and nutrients, creating a unique setting for the birth of life. The combination of heat, water, and a variety of chemical elements set the stage for the emergence of the first life forms. In this tumultuous environment, simple organic molecules began to form. These molecules, such as amino acids and nucleotides, are the building blocks of life. Over time, through a series of chemical reactions and environmental influences, these basic compounds evolved into more complex structures, eventually leading to the first primitive cells. This process of evolution from simple to complex is a fundamental aspect of how life developed on our planet. One of the key theories supporting the origins of life is the Miller-Urey experiment, conducted in the 1950s. This groundbreaking experiment simulated the conditions of early Earth by combining water, methane, ammonia, and hydrogen in a closed system. By applying electrical sparks to mimic lightning, the researchers were able to produce amino acids, demonstrating that organic molecules could form under the right conditions. This experiment provided crucial evidence that life could arise from non-living matter, igniting further research into the origins of life. As we explore these fascinating conditions and theories, we begin to unravel the mystery of how life took its first breath on our planet. The first creatures. The earliest known organisms on Earth were prokaryotic, meaning they lacked a nucleus and other membrane-bound organelles. These simple life forms, primarily bacteria and archaea, emerged around 3.5 billion years ago. Bacteria, with their diverse shapes and metabolic pathways, thrived in various environments, from deep-sea vents to hot springs. Archaea, often found in extreme conditions like salt lakes and hydrothermal vents, showcased the incredible adaptability of life. These prokaryotic organisms were not just the foundation of life. They played a crucial role in shaping the planet's ecosystems. One of the most significant developments in early life was the emergence of photosynthetic organisms, particularly cyanobacteria. These remarkable creatures harnessed sunlight to convert carbon dioxide and water into glucose and oxygen. This process not only provided energy for themselves, but also dramatically altered Earth's atmosphere. The oxygen produced by cyanobacteria led to the Great Oxygenation Event, transforming the planet and paving the way for aerobic life forms. This shift in atmospheric composition was a game-changer, allowing for the evolution of more complex organisms. As time progressed, multicellular organisms began to emerge, marking a significant evolutionary milestone. These early multicellular life forms, such as simple algae and sponges, offered several advantages over their unicellular counterparts. They could grow larger, specialize in different functions, and develop more complex structures. This specialization allowed for greater efficiency in resource use and survival strategies, setting the stage for the incredible diversity of life that would follow. The journey from simple prokaryotes to complex multicellular organisms illustrates the remarkable adaptability and resilience of life on Earth. Mass extinction events. Throughout Earth's history, several mass extinction events have dramatically reshaped the planet's biodiversity, leading to the disappearance of countless early creatures. Among the most significant of these events are the Ordovician-Silurian extinction, which occurred around 443 million years ago, and the Permian-Triassic extinction, approximately 252 million years ago. The Ordovician-Silurian extinction is believed to have wiped out nearly 85% of marine species, primarily due to drastic climate changes and a drop in sea levels. This event marked a pivotal moment in the evolution of life, as it opened ecological niches for new species to thrive. The Permian-Triassic extinction, often referred to as the Great Dying, was even more catastrophic, resulting in the loss of about 96% of all marine species and 70% of terrestrial vertebrates. This extinction event is attributed to a combination of factors, including massive volcanic eruptions, which released greenhouse gases and led to severe climate change, as well as potential asteroid impacts. The resulting environmental upheaval created conditions that many species could not survive. These mass extinction events had profound impacts on biodiversity and the evolution of life. While they caused widespread loss, they also paved the way for new species to emerge and diversify. After the Permian-Triassic extinction, for instance, the Triassic period saw the rise of dinosaurs and mammals, fundamentally altering the course of evolution. By examining these extinction events, we gain valuable insights into the resilience of life and the intricate balance of ecosystems throughout Earth's history. Survival and adaptation. In the face of mass extinction events, the concept of natural selection plays a crucial role in determining which species survive and thrive. Natural selection is the process by which organisms better adapted to their environment tend to survive and reproduce, passing on their advantageous traits to future generations. This mechanism of evolution allows species to adapt to changing conditions, making it a vital factor in the survival of early creatures during tumultuous times. After significant extinction events, certain groups of organisms demonstrated remarkable resilience and adaptability. For instance, reptiles and amphibians emerged as dominant life forms following the Permian-Triassic extinction. With their ability to thrive in diverse environments and their varied reproductive strategies, these creatures capitalized on the ecological niches left vacant by extinct species. Reptiles, in particular, diversified into numerous forms, eventually leading to the rise of dinosaurs, which would dominate the Mesozoic era. Another key factor in the survival of species is genetic diversity. A genetically diverse population is more likely to possess individuals with traits that can withstand environmental changes, diseases, and other challenges. This diversity acts as a buffer against extinction, allowing some members of a species to adapt to new conditions, while others may not. For example, the genetic variation seen in amphibians has enabled them to survive in various habitats, from rainforests to deserts, despite facing numerous threats. In summary, the interplay of natural selection, the adaptability of certain species, and the importance of genetic diversity has allowed some early creatures to not only survive, but also flourish in the aftermath of extinction events, shaping the evolutionary landscape of our planet. Lessons from extinction. Reflecting on the extinction of early creatures offers valuable insights into the current state of biodiversity and the environmental challenges we face today. By studying past extinction events, we can better understand the factors that led to the decline of species and the subsequent recovery of ecosystems. These historical lessons highlight the fragility of life and the delicate balance that sustains our planet. As we confront modern issues such as climate change, habitat destruction, and pollution, recognizing the patterns of past extinctions can guide us in making informed decisions to protect our environment. The importance of conservation efforts cannot be overstated. Just as early creatures faced catastrophic changes that led to their extinction, many species today are at risk due to human activities. Protecting habitats, implementing sustainable practices, and supporting biodiversity initiatives are crucial steps in preventing further extinctions. By prioritizing conservation, we not only safeguard individual species, but also preserve the intricate web of life that supports ecosystems and human well-being. Moreover, appreciating the interconnectedness of life on Earth is essential for fostering a sense of responsibility toward our environment. Every species, no matter how small, plays a role in maintaining ecological balance. The extinction of one species can have cascading effects on others, disrupting food chains and altering habitats. By recognizing our place within this interconnected system, we can cultivate a deeper respect for nature and a commitment to preserving it for future generations. In conclusion, the lessons learned from the extinction of early creatures serve as a powerful reminder of the importance of biodiversity and the urgent need for conservation efforts in our ever-changing world. The evolution of Earth's atmosphere and climate introduction. Welcome to our exploration of the fascinating evolution of Earth's atmosphere and climate. Imagine a time when our planet was a hostile environment filled with toxic gases and extreme conditions. In its early days, Earth's atmosphere was primarily composed of carbon dioxide, methane, and ammonia, making it inhospitable for life as we know it. However, over millions of years, a remarkable transformation took place. Through processes like volcanic activity and the emergence of photosynthetic organisms, particularly cyanobacteria, oxygen began to accumulate in the atmosphere. This gradual increase in oxygen levels paved the way for the development of complex life forms, ultimately leading to the rich biodiversity we see today. Understanding the various climate epochs is crucial for grasping how these changes have shaped life on Earth. From the warm greenhouse conditions of the Mesozoic era to the ice ages of the Pleistocene, each epoch has left its mark on the planet and its inhabitants. These shifts in climate not only influence the evolution of species, but also determine the distribution of ecosystems across the globe. As we delve into this captivating journey of Earth's atmospheric evolution, we'll uncover the intricate connections between climate, life, and the environment. By examining the past, we can gain valuable insights into our present and future, especially in the context of ongoing climate change. So, join us as we embark on this enlightening adventure through time, exploring how our planet transformed from a toxic wasteland into a vibrant, life-sustaining haven. The primordial atmosphere. In the earliest days of Earth, the atmosphere was a far cry from the life-sustaining blanket we know today. The primordial atmosphere was primarily composed of gases such as methane, ammonia, water vapor, and carbon dioxide. This toxic mix created an environment that was not only inhospitable but also dangerous for any potential life forms. The absence of free oxygen meant that the atmosphere lacked the essential element needed for most life, as we understand it. Volcanic activity played a significant role in shaping this early atmosphere. As the planet cooled, numerous volcanoes erupted, releasing vast amounts of gases into the air. These eruptions contributed to the high levels of carbon dioxide and sulfur dioxide, further intensifying the toxic nature of the atmosphere. The heat from these volcanic activities also led to the formation of a thick layer of clouds, trapping heat and creating a greenhouse effect that made the surface conditions even more extreme. The challenges posed by this primordial atmosphere were immense. With high concentrations of harmful gases and extreme temperatures, the chances of life emerging were slim. Any early organisms that might have existed would have had to withstand these harsh conditions, making the quest for life a daunting one. This toxic environment set the stage for a long and complex journey toward the development of a more hospitable atmosphere. Understanding these characteristics of Earth's early atmosphere helps us appreciate the incredible resilience of life and the transformative processes that eventually led to a thriving biosphere. The Great Oxygenation Event. The Great Oxygenation Event, often referred to as the oxygen catastrophe, marks a pivotal moment in Earth's history when the atmosphere underwent a dramatic transformation due to the production of oxygen. This monumental change was primarily driven by cyanobacteria, microscopic organisms that harnessed sunlight to produce energy through photosynthesis. As these ancient life forms thrived in the oceans, they began to release oxygen as a byproduct of their metabolic processes. Over millions of years, this gradual accumulation of oxygen in the atmosphere fundamentally altered the planet's environment. The rise in oxygen levels had profound implications for existing life forms. Prior to this event, most organisms were anaerobic, meaning they thrived in oxygen-free environments. As oxygen began to saturate the atmosphere and oceans, many of these anaerobic organisms faced extinction, unable to adapt to the new conditions. However, this shift also created opportunities for new life forms to emerge. The increasing availability of oxygen allowed for the evolution of aerobic organisms, which could utilize oxygen for respiration, leading to more efficient energy production. This transition not only paved the way for the development of complex multicellular life, but also set the stage for the diverse ecosystems we see today. The Great Oxygenation Event was a turning point that reshaped the trajectory of life on Earth, illustrating the intricate relationship between organisms and their environment. By understanding this critical event, we gain insight into the resilience of life and the dynamic processes that continue to influence our planet's atmosphere and climate. Climate epochs and their significance. Throughout Earth's history, several major climate epochs have played a crucial role in shaping the planet's atmosphere and the evolution of life. The Hadean epoch, which lasted from the formation of Earth around 4.6 billion years ago to about 4 billion years ago, was characterized by extreme volcanic activity and a molten surface. During this time, the atmosphere was thick with toxic gases, making it inhospitable for life. However, as the planet cooled, conditions began to stabilize, setting the stage for the next epoch. The Archean epoch followed, lasting from about 4 billion to 2.5 billion years ago. This period saw the emergence of the first simple life forms, primarily prokaryotic organisms like bacteria and archaea. The atmosphere began to change as cyanobacteria evolved, producing oxygen through photosynthesis. This gradual increase in oxygen levels marked the beginning of significant atmospheric transformation. Next came the Proterozoic epoch, spanning from 2.5 billion to about 541 million years ago. This epoch was marked by further increases in atmospheric oxygen and the development of more complex life forms. The rise of multicellular organisms during this time was closely linked to the changing climate and the availability of oxygen, which allowed for more complex metabolic processes. Each of these epochs illustrates the dynamic interplay between climate changes and the evolution of life. As atmospheric composition shifted, so too did the types of organisms that could thrive. Understanding these climate epochs not only provides insight into Earth's past, but also helps us comprehend the ongoing changes in our atmosphere and their potential impact on future life. Ice ages. A deep freeze. Ice ages are defined as prolonged periods of significant cooling on Earth, characterized by the expansion of continental ice sheets and glaciers. These geological markers are evident in the rock and sediment layers, showcasing the cyclical nature of glaciation and interglacial periods. An ice age can last for millions of years, with temperatures dropping enough to create vast ice sheets that cover large portions of the planet, profoundly impacting the climate and ecosystems. The effects of glaciation during ice ages are far-reaching. As glaciers advanced, they reshaped landscapes, carved valleys, and altered river systems. Ecosystems were dramatically affected, with many species forced to adapt to colder conditions or migrate to more hospitable areas. This led to significant evolutionary pressures, resulting in the emergence of new species and the extinction of others that could not cope with the changing environment. The flora and fauna had to adapt to the harsh conditions, leading to innovations in survival strategies, such as changes in diet and behavior. One of the most significant ice ages in Earth's history is the Pleistocene, which lasted from about 2.6 million to 11,700 years ago. During this time, massive ice sheets covered much of North America, Europe, and Asia. The Pleistocene is notable for the emergence of large mammals, such as woolly mammoths and saber-toothed cats, which adapted to the cold climate. The legacy of the Pleistocene Ice Age continues to influence modern ecosystems and biodiversity. Understanding these ice ages helps us appreciate the resilience of life and the ongoing impact of climate change on our planet. The greenhouse effect. A double-edged sword. The greenhouse effect is a natural process that plays a crucial role in regulating Earth's temperature and maintaining a habitable climate. It occurs when greenhouse gases, such as carbon dioxide, methane, and water vapor, trap heat in the atmosphere. When sunlight reaches the Earth, some of it is absorbed, warming the surface. The Earth then radiates this heat back into space, but greenhouse gases absorb and re-radiate some of this energy, effectively keeping the planet warm. Without this natural greenhouse effect, Earth would be too cold to support life as we know it. However, the balance between natural greenhouse effects and human-induced changes has become increasingly precarious. Over the past century, human activities, particularly the burning of fossil fuels and deforestation, have significantly increased the concentration of greenhouse gases in the atmosphere. This enhanced greenhouse effect leads to a rise in global temperatures, resulting in climate change. The consequences of this shift are far-reaching, affecting weather patterns, sea levels, and ecosystems worldwide. The implications of climate change on future atmospheric conditions are profound. As temperatures continue to rise, We can expect more frequent and severe weather events, such as hurricanes, droughts, and heat waves. Additionally, the melting of polar ice caps and glaciers contributes to rising sea levels, threatening coastal communities. Understanding the greenhouse effect and its dual nature is essential for addressing climate change. While it is vital for sustaining life, unchecked human influence can lead to catastrophic consequences for our planet and future generations. Balancing our impact on the atmosphere is crucial for ensuring a stable climate. The birth and death of stars. Have you ever gazed up at the night sky and wondered about the twinkling stars? Each one of those luminous points has a fascinating story to tell. A journey that begins with its birth in a stellar nursery and culminates in its dramatic death. The life cycle of stars is a captivating tale of stellar evolution, a process that not only shapes the cosmos, but also plays a crucial role in the formation of elements that make up everything around us, including ourselves. Understanding how stars evolve is significant for several reasons. For one, it helps us comprehend the very fabric of the universe. Stars are the universe's factories, forging elements like carbon, oxygen, and iron through nuclear fusion. When they reach the end of their lives, they explode in spectacular supernovae, scattering these elements across galaxies and seeding new stars and planets. By exploring the life cycle of stars, we gain insights into the origins of the universe and the intricate web of cosmic connections. So, buckle up as we embark on this stellar journey, unraveling the mysteries of how stars are born, live, and ultimately die, influencing galaxies and the very essence of life itself. Stellar nurseries. Stellar nurseries are the enchanting regions of space where stars are born, and they are often found within vast molecular clouds. These clouds are composed of gas and dust, primarily hydrogen, and are incredibly cold and dense. The conditions within these molecular clouds are perfect for star formation. As the gas and dust accumulate, they create pockets of higher density, which can trigger the gravitational collapse necessary for star birth. Gravity plays a pivotal role in this process. When a region within a molecular cloud becomes dense enough, the gravitational forces begin to pull the surrounding gas and dust inward. This collapse leads to the formation of a protostar, a hot, dense core that will eventually ignite nuclear fusion and become a fully fledged star. The surrounding material can also form a rotating disk, which may give rise to planets, moons, and other celestial bodies. Stellar nurseries are vital to the galactic ecosystem. They not only produce new stars, but also recycle materials back into the galaxy. The elements forged in stars are released into space when they die, enriching the interstellar medium and providing the building blocks for future generations of stars and planets. Understanding these nurseries helps us appreciate the dynamic processes that shape our universe. Protostar phase. The transition from a protostar to a main-sequence star is a fascinating journey that marks a critical phase in stellar evolution. During the protostar phase, a dense core forms within a collapsing molecular cloud, surrounded by an accretion disk of gas and dust. As material from this disk spirals inward, it adds mass to the protostar, increasing its temperature and pressure at the core. The defining moment of this phase occurs when nuclear fusion ignites in the core. As temperatures soar to millions of degrees, hydrogen atoms begin to fuse into helium, releasing an immense amount of energy in the process. This energy creates an outward pressure that counteracts the inward pull of gravity, stabilizing the star and marking its entry into the main sequence phase of its life cycle. Protostars exhibit unique characteristics, such as being cooler and dimmer than main sequence stars, often appearing as reddish or yellowish objects. The surrounding accretion disk plays a crucial role, not only in feeding the protostar, but also in potentially forming planets and other celestial bodies. This phase is significant because it sets the stage for a star's future. The mass and composition of the protostar will ultimately determine its lifespan, size, and the type of stellar phenomena it will experience later in life. Understanding this transition helps us grasp the complex processes that govern the life cycles of stars. Main sequence stars. The main sequence phase is the longest and most stable period in a star's life cycle, lasting millions to billions of years, depending on the star's mass. During this phase, stars achieve a delicate balance between the inward pull of gravity and the outward pressure generated by nuclear fusion occurring in their cores. This equilibrium is crucial. If gravity were to overpower fusion, the star would collapse, while excessive fusion would lead to an explosive expansion. Main sequence stars can be categorized into different types based on their mass and temperature. The hottest and most massive stars, known as O-type stars, burn brightly and quickly, while cooler, less massive stars, like M-type stars, shine dimly and live much longer. Our Sun is classified as a G-type star, sitting comfortably in the middle of this spectrum. Main sequence stars play a vital role in the cosmic ecosystem, particularly in the creation of heavier elements. Through the process of nuclear fusion, they convert hydrogen into helium and, in later stages, can fuse helium into heavier elements like carbon and oxygen. These elements are essential for the formation of planets and life as we know it. Understanding main sequence stars helps us appreciate their significance in the universe's ongoing cycle of creation and destruction. Red giants and supergiants. As stars exhaust their hydrogen fuel, they undergo a dramatic transformation, evolving into red giants or supergiants. This phase marks a significant shift in a star's life cycle. When hydrogen in the core is depleted, nuclear fusion slows down, causing the core to contract under gravity. This contraction raises the core's temperature, eventually igniting helium fusion. Meanwhile, the outer layers of the star expand and cool, giving rise to the characteristic reddish hue of red giants and the even larger, more luminous supergiants. During this phase, helium fusion begins, converting helium into heavier elements like carbon and oxygen. In the case of massive stars, the fusion process continues, creating even heavier elements through a series of nuclear reactions. This stellar alchemy is crucial, as it produces the elements that will later be dispersed into space when the star reaches the end of its life. The significance of these stages cannot be overstated. For massive stars, the transition to red giant or supergiant is a precursor to their explosive deaths, often culminating in supernovae. These cataclysmic events not only enrich the interstellar medium with heavy elements, but also trigger the formation of new stars and planetary systems. Understanding this evolution helps us grasp the intricate processes that shape our universe and the elements that compose it. Supernovae. The explosive death of massive stars culminates in a spectacular event known as a supernova. This cataclysmic explosion occurs when a star has exhausted its nuclear fuel, leading to a dramatic collapse of its core. There are two primary types of supernovae. Type 1, which results from the thermonuclear explosion of a white dwarf in a binary system, and Type 2, which occurs when a massive star's core collapses under gravity after it has depleted its nuclear fuel. In both cases, the energy released is immense, outshining entire galaxies for a brief period. Supernovae have a profound impact on their surrounding space. The explosion generates shock waves that can trigger the formation of new stars by compressing nearby gas and dust. Additionally, the intense heat and energy from the explosion disperse heavy elements, such as iron, nickel, and other vital building blocks for planets and life into the interstellar medium. The role of supernovae in enriching the interstellar medium is crucial. As these explosions scatter elements across vast distances, they contribute to the cosmic recycling process, allowing new stars and planetary systems to form from the remnants of previous generations. Understanding supernovae not only illuminates the life cycles of stars, but also highlights their significance in the ongoing evolution of the universe. Neutron stars and black holes. After a supernova explosion, the remnants of massive stars can evolve into two fascinating entities: neutron stars and black holes. Neutron stars form when the core of a massive star collapses under gravity, compressing protons and electrons into neutrons. This results in an incredibly dense object, where a sugar cube-sized amount of neutron star material would weigh about 1 billion tons. Neutron stars possess unique properties, including rapid rotation and strong magnetic fields, often emitting beams of radiation that can be detected as pulsars. On the other hand, black holes are formed when the core's collapse continues beyond the neutron star stage, leading to a point of infinite density known as a singularity. The gravitational pull of a black hole is so strong that not even light can escape its grasp, making them invisible to direct observation. Their presence is inferred through their effects on nearby matter, such as the acceleration of stars in their vicinity or the emission of X-rays from material falling into them. The significance of these remnants in the cosmic landscape is profound. Neutron stars and black holes serve as laboratories for extreme physics, helping scientists understand fundamental forces and the nature of matter. Additionally, they play a crucial role in the evolution of galaxies, influencing star formation and the dynamics of cosmic structures. Element creation and galactic impact. Stellar evolution plays a pivotal role in the creation of elements through processes known as nucleosynthesis. In the cores of stars, lighter elements like hydrogen and helium undergo fusion to form heavier elements, such as carbon, oxygen, and iron. This process continues until a star reaches the end of its life, culminating in a supernova explosion. During this explosive event, even heavier elements, like gold and uranium, are forged and dispersed into the surrounding space, enriching the interstellar medium with essential building blocks for future stars and planets. The importance of these elements cannot be overstated. They are fundamental in forming planets and, ultimately, life itself. For instance, carbon is a key component of organic molecules, while oxygen is vital for respiration in many life forms. The elements produced in stars and released during supernovae create the chemical diversity necessary for the development of complex structures in the universe. Moreover, the deaths of stars significantly influence galactic structure and evolution. Supernovae can trigger new star formation by compressing nearby gas clouds, while the remnants of massive stars, such as neutron stars and black holes, can affect the dynamics of their host galaxies. This interplay of stellar life and death shapes the cosmic landscape, driving the ongoing cycle of creation and destruction that defines our universe. The Cambrian explosion and rise of complex life. The Cambrian explosion marks one of the most significant events in the history of life on Earth, occurring around 541 million years ago. This remarkable period is characterized by a rapid diversification of life forms, leading to the emergence of complex organisms that would shape the planet's biological landscape. Before this explosion, life was predominantly simple and microscopic, consisting mainly of single-celled organisms. However, during the Cambrian period, we witness an astonishing array of new species, including the first representatives of many major animal groups we recognize today. What makes the Cambrian explosion so captivating is not just the sheer number of new life forms, but also the complexity and variety that emerged in such a short time. Imagine a world where the oceans were teeming with bizarre creatures, some with hard shells, others with intricate body structures, and many that were unlike anything we see today. This period set the stage for the evolution of more advanced life forms, including vertebrates, which would eventually lead to the rise of mammals and, ultimately, humans. As we delve into the mysteries of the Cambrian explosion, we uncover not only the excitement of life's diversification, but also the intricate relationships and ecosystems that began to form. The complexity of these early life forms raises intriguing questions about how they adapted and thrived in their environments. Join us as we explore this fascinating chapter in evolutionary history, revealing the wonders of life's early days and the profound impact it has had on the world we know today. What was the Cambrian explosion? The Cambrian explosion refers to a pivotal period in Earth's history, occurring approximately 541 million years ago, during which life underwent an extraordinary diversification. This era marks the transition from predominantly simple, single-celled organisms to a vibrant array of complex, multicellular life forms. Spanning roughly 20 million years, the Cambrian period is often celebrated as the cradle of modern biodiversity, setting the stage for the evolutionary developments that followed. Key fossil discoveries from this time provide compelling evidence of the rapid emergence of various life forms. One of the most famous sites is the Burgess Shale in Canada, where fossils of soft-bodied organisms have been remarkably preserved. Here, paleontologists have uncovered a treasure trove of species, including the enigmatic Hallucigenia and the early arthropod Anomalocaris, which showcase the bizarre and diverse forms that thrived during this period. These fossils not only highlight the variety of life, but also reveal the intricate ecosystems that began to develop in the oceans. The significance of the Cambrian explosion in evolutionary biology cannot be overstated. It represents a critical juncture where the foundations of complex life were laid, leading to the establishment of major animal groups that would dominate the planet for millions of years. This event challenges our understanding of evolutionary processes, suggesting that rapid changes can occur under certain environmental conditions. By studying the Cambrian explosion, scientists gain valuable insights into the mechanisms of evolution, adaptation, and the interconnectedness of life, making it a cornerstone of biological research and a fascinating topic for exploration. Major developments in organisms. During the Cambrian period, the emergence of complex organisms marked a transformative phase in the history of life on Earth. This era saw the appearance of several major groups of organisms, including arthropods, mollusks, and early chordates. Arthropods, characterized by their segmented bodies and jointed limbs, became one of the most successful and diverse groups, giving rise to insects, crustaceans, and arachnids. Mollusks, which include snails, clams, and cephalopods, also made their debut, showcasing a variety of forms and adaptations that would later flourish in different environments. One of the most significant developments during the Cambrian period was the evolution of hard body parts, such as shells and exoskeletons. These structures provided crucial evolutionary advantages, including protection from predators and environmental hazards. The hard parts also facilitated movement and allowed organisms to occupy new ecological niches. For instance, the hard shells of mollusks not only offered defense, but also enabled them to burrow into substrates, enhancing their survival in diverse habitats. These major developments set the stage for future biodiversity by establishing complex interactions within ecosystems. The rise of predatory organisms, enabled by hard body parts, led to evolutionary arms races, driving adaptations in both predators and prey. This dynamic environment fostered innovation in body plans and behaviors, paving the way for the vast array of life forms that would follow. The Cambrian period laid the groundwork for the intricate web of life we see today, illustrating how evolutionary advancements can lead to an explosion of diversity and complexity in the natural world. Ecological changes. Leading to diversification, the Cambrian explosion was not just a biological phenomenon, it was also deeply influenced by a variety of ecological factors that contributed to the rapid diversification of life. One of the most significant changes during this period was the alteration in ocean chemistry, particularly the increase in oxygen levels. As photosynthetic organisms proliferated, oxygen became more abundant in the oceans, creating an environment conducive to the development of larger and more complex life forms. Higher oxygen levels allowed for more efficient respiration and energy production, enabling organisms to grow larger and evolve more intricate body structures. Another crucial factor was the emergence of diverse ecological niches and the dynamics of predator-prey relationships. As new species evolved, they began to occupy various ecological roles, leading to a complex web of interactions. The rise of predatory organisms created selective pressures that drove adaptations in prey species, resulting in an evolutionary arms race. This dynamic interaction not only spurred innovation in body plans and defenses, but also contributed to the overall diversification of life during the Cambrian period. Additionally, continental drift played a significant role in shaping habitats and influencing biodiversity. As landmasses shifted and separated, new environments emerged, providing opportunities for organisms to adapt and evolve in response to varying conditions. The availability of different habitats, such as shallow seas and coastal areas, allowed for the exploration of new ecological niches, further fueling diversification. Together, these ecological changes created a rich tapestry of life during the Cambrian explosion, setting the stage for the complex ecosystems that would follow in the evolutionary timeline. The role of genetic innovation. The Cambrian explosion was not only a time of ecological and environmental change, but also a period marked by significant genetic innovation that facilitated the rise of complex life. Genetic mutations played a crucial role during this time, introducing variations that allowed organisms to adapt to new challenges and opportunities. These mutations, whether beneficial or neutral, provided the raw material for evolution, enabling species to explore new forms and functions. As a result, the genetic diversity that emerged during this period laid the groundwork for the complex life forms we see today. Developmental biology also played a pivotal role in shaping the body plans of organisms during the Cambrian period. The evolution of regulatory genes, such as Hox genes, allowed for more intricate patterns of development, leading to the emergence of diverse body structures. These genes dictate the arrangement of body segments and the formation of specialized structures, enabling organisms to develop unique adaptations that suited their environments. The ability to modify body plans through genetic regulation was a game-changer, allowing for the rapid evolution of new forms. These genetic factors contributed to increased complexity in organisms, as they enabled the development of specialized tissues, organs, and systems. As organisms became more complex, they could occupy various ecological niches, interact in more sophisticated ways, and respond to environmental changes more effectively. This genetic innovation not only fueled the diversification of life during the Cambrian explosion, but also set the stage for the intricate biological systems that would evolve in the millions of years that followed, highlighting the profound impact of genetics on the history of life on Earth. Impact on modern biodiversity. The Cambrian explosion was a transformative event that laid the foundation for modern ecosystems and the incredible biodiversity we observe today. This period marked the emergence of many major animal groups, establishing evolutionary lineages that continue to thrive and evolve. For instance, the arthropods, which first appeared during the Cambrian, have diversified into a vast array of species, including insects, crustaceans, and arachnids. Similarly, mollusks, which also made their debut during this time, have given rise to a wide variety of forms, from snails to octopuses. These lineages not only contribute to the richness of life on Earth, but also play essential roles in their respective ecosystems. Understanding the Cambrian explosion is crucial for conservation efforts today. By studying the origins and evolutionary trajectories of modern species, scientists can gain insights into how ecosystems function and how they respond to environmental changes. This knowledge is vital for developing effective conservation strategies, especially in the face of current biodiversity loss driven by habitat destruction, climate change, and pollution. Recognizing the interconnectedness of life and the historical context of modern biodiversity can help inform policies aimed at preserving ecosystems and the myriad species they support. Moreover, the Cambrian explosion serves as a reminder of life's resilience and adaptability. As we face unprecedented challenges in the natural world, understanding the evolutionary processes that shaped our planet can inspire innovative solutions for conservation. By appreciating the significance of this pivotal event, we can better protect the intricate web of life that has evolved over millions of years and ensure its survival for future generations. Mass extinctions. Throughout Earth's history, mass extinctions are some of the most dramatic events in Earth's history, marking significant turning points in the evolution of life. Over the past 500 million years, scientists have identified 5 major mass extinction events that reshaped the planet's biodiversity. The first, known as the Ordovician-Silurian extinction, occurred around 440 million years ago, wiping out nearly 85% of marine species. Next came the late Devonian extinction, which unfolded over several million years and led to the loss of about 75% of species, primarily affecting marine life. The most famous of these events is the Permian-Triassic extinction, often referred to as the Great Dying, which occurred around 252 million years ago and eliminated approximately 96% of all species. Following that, the Triassic-Jurassic extinction around 201 million years ago set the stage for the rise of dinosaurs, while the Cretaceous-Paleogene extinction, about 66 million years ago, famously led to the demise of the dinosaurs and allowed mammals to flourish. Understanding these mass extinctions is crucial for several reasons. They reveal the fragility of ecosystems and the interconnectedness of life on Earth. By studying these events, we can gain insights into how species adapt, evolve, and sometimes fail to survive in the face of dramatic environmental changes. The rise and fall of species during these periods highlight the resilience of life, showcasing how new forms of life can emerge from the ashes of extinction. This knowledge not only enriches our understanding of Earth's history, but also serves as a warning for the future as we face ongoing environmental challenges. The Ordovician-Silurian extinction. The Ordovician-Silurian extinction, occurring around 440 million years ago, marks the first of the 5 major mass extinction events in Earth's history. This event was primarily driven by significant climate change and dramatic fluctuations in sea levels. During this period, the Earth experienced a cooling phase that led to the formation of glaciers, particularly in the southern hemisphere. As ice sheets expanded, sea levels dropped, drastically altering marine habitats. This fluctuation created a challenging environment for many marine species, which were unable to adapt quickly enough to the changing conditions. The impact of this extinction event was profound, particularly for marine life. Approximately 85% of all marine species vanished, with notable losses among groups like trilobites and brachiopods. Trilobites, once abundant and diverse, faced severe declines, while brachiopods, which thrived in the Ordovician seas, also suffered significant losses. The extinction of these key species disrupted the marine food web, leading to a cascade of ecological consequences that reshaped the oceanic landscape. Despite the devastation, the Ordovician-Silurian extinction set the stage for future biodiversity. The aftermath of this event allowed for the emergence of new species and groups that would fill the ecological niches left vacant by the extinctions. This period of recovery fostered the evolution of more complex marine ecosystems, paving the way for the rich diversity of life that would follow in the Silurian and beyond. Understanding this event helps us appreciate the resilience of life and the intricate balance of ecosystems throughout Earth's history. The Late Devonian Extinction. The Late Devonian extinction, which unfolded over a span of approximately 20 million years, around 375 million years ago, is characterized by a series of environmental upheavals that significantly impacted life on Earth. One of the primary causes of this extinction event was the occurrence of anoxic events, where large portions of the ocean became depleted of oxygen. These anoxic conditions were likely exacerbated by climate changes, including fluctuations in temperature and sea level, which disrupted marine ecosystems and led to widespread habitat loss. The decline of reef ecosystems during this period was particularly notable. Coral reefs, which had flourished in the Devonian seas, began to deteriorate due to the changing environmental conditions. This decline had a cascading effect on fish species that relied on these reefs for shelter and food. As reefs vanished, many fish populations plummeted, leading to a significant loss of biodiversity in marine environments. The extinction of key reef-building organisms, such as certain corals and stromatoporoids, further destabilized these ecosystems. The long-term effects of the late Devonian extinction were profound, influencing both terrestrial and marine life for millions of years. The loss of biodiversity created opportunities for new species to evolve and fill the ecological niches left vacant by the extinctions. On land, the decline of certain plant groups affected the development of terrestrial ecosystems, while in the oceans, the extinction of many marine species paved the way for the rise of new groups, including early amphibians and more advanced fish. This event serves as a reminder of the interconnectedness of life and the delicate balance that sustains ecosystems throughout Earth's history. The Permian-Triassic extinction. The Permian-Triassic extinction, often referred to as the Great Dying, stands as the most severe mass extinction event in Earth's history, occurring around 252 million years ago. This catastrophic event is believed to have been triggered by a combination of factors, including massive volcanic eruptions in the Siberian Traps, which released vast amounts of carbon dioxide and sulfur dioxide into the atmosphere. These eruptions led to significant climate changes, including global warming and acid rain. Additionally, the release of methane from oceanic methane clathrates further exacerbated the situation, creating a toxic environment that many species could not survive. The consequences of the Permian-Triassic extinction were staggering, with estimates suggesting that up to 90% of marine life and 70% of terrestrial vertebrate species were lost. This included the extinction of many dominant groups, such as trilobites, ammonites, and various types of plants. The loss of biodiversity during this period was unprecedented, leading to a dramatic reshaping of ecosystems across the globe. Despite the devastation, the recovery from the Permian-Triassic extinction eventually paved the way for the rise of new life forms in the Triassic period. As ecosystems began to stabilize, new species emerged, including the first dinosaurs and mammals. This period of recovery was crucial, as it allowed for the diversification of life that would dominate the Mesozoic era. The Permian-Triassic extinction serves as a powerful reminder of the resilience of life and the potential for recovery following catastrophic events, shaping the evolutionary trajectory of future species on Earth. The Triassic-Jurassic extinction. The Triassic-Jurassic extinction, which occurred around 201 million years ago, was a pivotal event that significantly altered the course of life on Earth. Several factors contributed to this extinction, with climate change and volcanic activity playing crucial roles. During this period, extensive volcanic eruptions in the Central Atlantic Magmatic Province released large amounts of carbon dioxide and other gases into the atmosphere. This led to a rapid increase in global temperatures and disrupted established climate patterns, creating harsh conditions for many species. As the environment changed, the dominant reptiles of the Triassic period faced significant challenges. The stress from climate fluctuations and habitat loss contributed to the decline of various reptilian groups, paving the way for the rise of dinosaurs. These early dinosaurs were able to adapt to the changing conditions, taking advantage of the ecological niches left vacant by the extinctions. This transition marked a significant shift in the dynamics of terrestrial ecosystems as dinosaurs began to dominate the landscape. The impact of the Triassic-Jurassic extinction on biodiversity and ecosystem dynamics was profound. With the loss of many species, ecosystems underwent significant restructuring, allowing for the emergence of new life forms. The extinction event created opportunities for the diversification of dinosaurs, which would go on to become the dominant terrestrial vertebrates for the remainder of the Mesozoic era. Additionally, the recovery period following this extinction laid the groundwork for the development of more complex ecosystems, ultimately shaping the evolutionary trajectory of life on Earth. The Triassic-Jurassic extinction serves as a reminder of the interconnectedness of climate, species, and ecosystems throughout history. The Cretaceous-Paleogene extinction. The Cretaceous-Paleogene extinction, which occurred approximately 66 million years ago, is one of the most well-known mass extinction events in Earth's history, primarily due to the dramatic impact it had on life. The leading cause of this extinction is widely believed to be a massive asteroid impact near the present-day Yucatan Peninsula in Mexico. This impact created the Chicxulub crater and unleashed catastrophic effects on the planet's climate. The immediate aftermath included intense heat, wildfires, and a nuclear winter scenario where dust and debris blocked sunlight, leading to a significant drop in temperatures and disrupting photosynthesis. The consequences of this event were profound, resulting in the extinction of approximately 75% of all species, including the non-avian dinosaurs that had dominated terrestrial ecosystems for millions of years. The loss of these large reptiles opened up ecological niches, allowing mammals, which had previously been small and relatively insignificant, to diversify and evolve into a wide range of forms. This shift marked the beginning of the Age of Mammals, leading to the eventual emergence of many modern mammalian groups. The Cretaceous-Paleogene extinction was crucial in shaping modern ecosystems. The extinction of dominant species like dinosaurs allowed for the proliferation of mammals and birds, leading to the complex ecosystems we see today. This event serves as a pivotal moment in evolutionary history, illustrating how catastrophic changes can lead to new opportunities for life to flourish. Understanding the causes and consequences of this extinction helps us appreciate the resilience of life and the intricate balance of ecosystems that continue to evolve on our planet. Humans and Earth's future extinctions. The Anthropocene epoch marks a significant period in Earth's history, characterized by the profound impact of human activities on the planet's ecosystems. This term, which has gained traction in scientific and environmental discussions, refers to the current geological age, where human influence is the dominant force shaping the environment. Unlike previous epochs, the Anthropocene highlights how our actions, ranging from industrialization to urbanization, have led to unprecedented changes in climate, land use, and biodiversity. As we delve into this topic, it's crucial to recognize the alarming rates of extinction that have escalated during this epoch. Human activities, such as deforestation, pollution, and overfishing, have drastically altered habitats and disrupted the delicate balance of ecosystems. According to scientists, species are currently going extinct at a rate 1,000 times faster than the natural background rate, a trend that poses a dire threat to global biodiversity. This loss not only affects the species themselves, but also jeopardizes the services they provide, such as pollination, clean water, and climate regulation. Understanding the implications of the Anthropocene is urgent. As stewards of the planet, we must confront the reality that our choices today will shape the future of life on Earth. Engaging with these issues is not just an academic exercise, it's a call to action. By raising awareness and fostering discussions about our impact on the environment, we can inspire collective efforts to mitigate these challenges and work towards a sustainable future for all living beings. Understanding the Anthropocene epoch. The Anthropocene epoch is a term used to describe the current geological age, characterized by the significant and lasting impact of human activities on the Earth's geology and ecosystems. While the exact starting point of the Anthropocene is debated, many scientists suggest it began in the mid-20th century, coinciding with the post-World War II boom in industrialization, population growth, and technological advancement. This period has seen humans become a dominant force in shaping the planet, altering landscapes, climates, and biodiversity in ways previously unimaginable. Several markers distinguish the Anthropocene from previous geological epochs. One of the most notable is the dramatic increase in greenhouse gas concentrations in the atmosphere, primarily due to fossil fuel combustion and deforestation. This has led to climate change, which is reshaping weather patterns and affecting ecosystems worldwide. Additionally, the proliferation of plastics and other synthetic materials has left a lasting imprint on the geological record, with microplastics now found in even the most remote environments. Human influence has become a geological force, as evidenced by the changes we've made to the Earth's surface. Urbanization has transformed vast areas into cities, while agriculture has altered landscapes to meet food demands. Furthermore, the extinction of numerous species due to habitat destruction and pollution highlights our role in the ongoing biodiversity crisis. As we navigate the complexities of the Anthropocene, it's essential to recognize our responsibility in shaping the future of the planet and to consider how our actions can lead to a more sustainable coexistence with nature. Human activities. Driving extinction. Human activities are at the forefront of the ongoing extinction crisis, with several key factors contributing to the alarming decline in biodiversity. One of the most significant drivers is habitat destruction, which occurs when natural environments are altered or eliminated to make way for agriculture, urban development, and infrastructure projects. This loss of habitat not only reduces the living space available for countless species, but also fragments ecosystems, making it difficult for animals and plants to thrive and reproduce. Pollution is another critical factor impacting species survival. Contaminants such as plastics, heavy metals, and chemicals seep into ecosystems, poisoning wildlife and disrupting reproductive systems. Water pollution, in particular, has devastating effects on aquatic life, leading to declines in fish populations and the degradation of coral reefs. As pollution continues to accumulate, its long-term effects on biodiversity become increasingly severe. Climate change, driven largely by human activities, poses an additional threat to species around the globe. Rising temperatures, shifting weather patterns, and extreme weather events disrupt habitats and force species to adapt or migrate. Many species struggle to keep pace with these rapid changes, leading to increased vulnerability and extinction. Overexploitation of resources, including overfishing, hunting, and logging, further exacerbates the crisis. Unsustainable practices deplete populations of various species, pushing them closer to extinction. Additionally, the introduction of invasive species, often a result of human trade and travel, disrupts local ecosystems, outcompeting native species for resources and altering food webs. Together, these human activities create a perfect storm for extinction, underscoring the urgent need for conservation efforts and sustainable practices to protect our planet's biodiversity. Case studies of extinction events. Examining specific case studies of extinction events provides a stark illustration of the impact human activities have on biodiversity. One of the most infamous examples is the passenger pigeon, once one of the most abundant birds in North America. By the late 19th century, relentless hunting and habitat destruction led to its rapid decline. The last known passenger pigeon, named Martha, died in captivity in 1914, marking a tragic end to a species that once numbered in the billions. This extinction serves as a cautionary tale about the consequences of unchecked human exploitation and the importance of conservation efforts. Currently, the Amur leopard stands on the brink of extinction, with fewer than 100 individuals remaining in the wild. Native to the temperate forests of the Russian Far East and northeastern China, this elusive big cat faces numerous threats, including habitat loss due to logging and agricultural expansion, poaching for its beautiful fur, and a decline in prey species. Conservationists are working tirelessly to protect the remaining population, but the Amur leopard's future remains uncertain as human encroachment continues to threaten its habitat. In marine environments, coral bleaching has emerged as a significant issue affecting biodiversity. Rising sea temperatures, primarily driven by climate change, cause corals to expel the symbiotic algae that provide them with color and nutrients. This phenomenon not only leads to the death of coral reefs, but also disrupts entire marine ecosystems that rely on these habitats for shelter and food. The decline of coral reefs has far-reaching implications for marine biodiversity, affecting countless species and the livelihoods of communities that depend on healthy oceans. These case studies highlight the urgent need for action to address human impacts on the planet's biodiversity. The role of conservation efforts. Conservation efforts play a crucial role in preventing future extinctions and safeguarding the planet's biodiversity. One of the most effective strategies is the establishment of protected areas and wildlife reserves. These designated spaces provide safe havens for endangered species, allowing them to thrive without the pressures of habitat destruction, poaching, and human encroachment. By preserving critical habitats, protected areas not only support individual species, but also maintain the ecological balance necessary for healthy ecosystems. Numerous successful conservation programs have demonstrated the positive outcomes of dedicated efforts. For instance, the recovery of the gray wolf in Yellowstone National Park showcases how targeted conservation initiatives can restore ecosystems. After being reintroduced in the mid-1990s, gray wolves helped regulate elk populations, which in turn allowed vegetation to flourish and improved overall biodiversity in the park. Similarly, the conservation of the California condor, once on the brink of extinction, has seen the population rebound due to captive breeding programs and habitat protection. These success stories highlight the potential for conservation to make a tangible difference in reversing the trends of extinction. Community involvement and awareness are also vital components of effective conservation efforts. Engaging local communities in conservation initiatives fosters a sense of ownership and responsibility for the environment. Educational programs can raise awareness about the importance of biodiversity and the threats posed by human activities. By empowering individuals to participate in conservation, whether through volunteering, advocacy, or sustainable practices, we can create a collective movement toward protecting our planet. Ultimately, the success of conservation efforts hinges on collaboration between governments, organizations, and communities, working together to ensure a sustainable future for all species. Future Outlook. What lies ahead? As we look to the future, the outlook for biodiversity and extinction rates largely hinges on the choices we make today. Current human activities, such as deforestation, pollution, and climate change, paint a concerning picture. If these trends continue unchecked, we could witness a dramatic increase in extinction rates, with countless species facing the threat of disappearance. Scenarios range from the loss of iconic species, like elephants and tigers, to the collapse of entire ecosystems, which would have cascading effects on food security and human health. However, there is still hope. The importance of sustainable practices cannot be overstated. Transitioning to renewable energy sources, implementing sustainable agriculture, and promoting responsible consumption can significantly reduce our ecological footprint. By adopting practices that prioritize environmental health, we can create a more balanced relationship with nature. Sustainable practices not only help preserve biodiversity, but also ensure that natural resources are available for future generations. Encouraging proactive measures is essential to mitigate extinction risks. This includes supporting conservation initiatives, advocating for stronger environmental policies, and investing in research to understand the impacts of human activities on ecosystems. Community engagement plays a vital role in these efforts, as local knowledge and participation can lead to more effective conservation strategies. Ultimately, the future of biodiversity is not predetermined. It is shaped by our actions. By prioritizing sustainability and taking proactive steps to protect our planet, we can foster a healthier environment where both humans and wildlife can thrive. The choices we make today will determine the legacy we leave for future generations, making it imperative to act now to safeguard the rich tapestry of life on Earth. The formation of the Milky Way galaxy. The formation of the Milky Way galaxy is a captivating journey that spans billions of years, intertwining cosmic events and the birth of stars. Our galaxy, a vast collection of stars, gas, dust, and dark matter, began its life as a swirling cloud of primordial material shortly after the Big Bang. Over time, gravity pulled this matter together, leading to the formation of the first stars and clusters. These early stars played a crucial role in shaping the galaxy, as they exploded in supernovae, enriching the surrounding gas with heavier elements and paving the way for new star formation. The Milky Way is structured like a spiral, with its arms extending outward from a dense central bulge. This beautiful design is not just visually stunning. It also tells us about the dynamic processes that continue to shape our galaxy today. Understanding the Milky Way's structure and formation helps us grasp our place in the universe, revealing how galaxies evolve and interact over time. But the Milky Way is more than just a collection of stars and dust. It is a treasure trove of mysteries waiting to be uncovered. From the enigmatic dark matter that makes up a significant portion of its mass to the supermassive black hole at its center, the Milky Way holds secrets that challenge our understanding of physics and cosmology. As we delve deeper into the wonders of our galaxy, we not only learn about its history, but also about the fundamental nature of the universe itself. Join us as we explore the fascinating story of the Milky Way, and the mysteries that lie within its vast expanse. The birth of the Milky Way. The initial formation of the Milky Way galaxy is a fascinating tale that begins with primordial gas clouds and dark matter, the building blocks of our universe. Shortly after the Big Bang, the universe was filled with hydrogen and helium gas, along with a mysterious substance known as dark matter. While we cannot see dark matter directly, it exerts a gravitational influence that plays a crucial role in the formation of galaxies. These primordial gas clouds began to clump together under the force of gravity, creating regions of higher density that would eventually lead to the birth of stars and galaxies. As these gas clouds collapsed, gravitational forces intensified, leading to the formation of the galaxy's early structure. The process was not uniform. Some areas became denser and hotter, igniting nuclear fusion and giving birth to the first stars. These stars, in turn, influenced their surroundings, creating a dynamic environment where new stars could form and evolve. This interplay of gravitational forces and stellar activity laid the groundwork for the Milky Way's spiral structure. During this early phase, protogalaxies emerged, massive clouds of gas and dark matter that would eventually evolve into galaxies. These protogalaxies were significant because they represented the initial stages of galaxy formation, where the seeds of future structures were sown. Understanding these processes helps us piece together the history of the Milky Way and provides insight into how galaxies like ours came to be. The birth of the Milky Way is not just a story of stars and gas, it is a testament to the intricate dance of forces that shaped our cosmic home. Galactic structure. The Milky Way galaxy is a complex and beautiful system composed of several distinct components, each playing a vital role in its overall structure. At the center lies the bulge, a dense region filled with older stars, gas, and dust. This bulge is home to a supermassive black hole known as Sagittarius, a star, which exerts a powerful gravitational influence on the surrounding stars. The bulge serves as the heart of the galaxy, anchoring its structure and influencing the motion of stars within its vicinity. Surrounding the bulge is the disk, a flat, rotating region that contains the majority of the galaxy's stars, including young, bright stars and star clusters. The disk is characterized by its spiral arms, which are regions of higher density where stars and gas are concentrated. These spiral arms are significant because they are sites of active star formation, where new stars are born from the gas and dust that accumulate in these areas. The beauty of the Milky Way's spiral structure is not just aesthetic. It also plays a crucial role in the dynamics of the galaxy, guiding the movement of stars and facilitating the exchange of materials. Beyond the disk lies the halo, a spherical region that contains older stars, globular clusters, and a significant amount of dark matter. Dark matter, which makes up a large portion of the galaxy's mass, is invisible and does not emit light, yet it exerts a gravitational pull that influences the motion of stars and the overall structure of the Milky Way. Understanding these components and their interactions helps us appreciate the intricate architecture of our galaxy and the forces that shape it. Star formation and evolution. The process of star formation within the Milky Way is a remarkable journey that begins in the heart of nebulae, vast clouds of gas and dust scattered throughout the galaxy. These nebulae serve as the stellar nurseries where new stars are born. When regions within a nebula become dense enough, gravity pulls the gas and dust together, leading to the formation of protostars. As these protostars accumulate mass, they heat up and eventually ignite nuclear fusion in their cores, marking the birth of a new star. Once a star is born, it enters a life cycle that can span millions to billions of years, depending on its mass. Massive stars burn brightly and quickly, exhausting their nuclear fuel in a relatively short time. In contrast, smaller stars, like our Sun, have longer lifespans, gradually evolving through various stages until they reach the end of their life cycle. When massive stars exhaust their fuel, they undergo dramatic transformations, culminating in a supernova explosion. This cataclysmic event not only marks the death of the star, but also plays a crucial role in the galaxy's evolution. Supernovae are significant because they disperse heavy elements into the surrounding space, enriching the interstellar medium with materials necessary for the formation of new stars and planets. This cycle of birth, evolution, and death of stars contributes to the dynamic nature of the Milky Way, ensuring a continuous process of star formation. By understanding how stars are formed and evolve, we gain insight into the intricate workings of our galaxy and the cosmic processes that shape the universe. The Milky Way's place in the universe. To understand the Milky Way's significance, we must contextualize it within the larger cosmos. Our galaxy is part of a collection known as the Local Group, which consists of over 50 galaxies, including some of our closest neighbors. The most prominent of these is the Andromeda Galaxy, a spiral galaxy similar in structure to our own. Andromeda is on a collision course with the Milky Way, and in about 4.5 billion years, the two galaxies are expected to merge, creating a new, larger galaxy. This interaction highlights the dynamic nature of galaxies and the gravitational forces that govern their movements. Beyond the local group, galaxies are organized into larger structures known as galactic clusters. These clusters can contain dozens to hundreds of galaxies bound together by gravity. The Milky Way is part of the Virgo cluster, which is one of the most studied clusters in the universe. Clusters like Virgo serve as laboratories for understanding galaxy formation and evolution, as they provide insights into how galaxies interact and evolve over time. On an even grander scale, galactic clusters are grouped into superclusters, which are the largest known structures in the universe. The Milky Way resides in the Laniakea supercluster, a vast region that encompasses thousands of galaxies. This positioning within the supercluster emphasizes the interconnectedness of galaxies and the complex web of gravitational interactions that shape the universe. By exploring the Milky Way's place in this cosmic landscape, we gain a deeper appreciation for our galaxy's role in the grand tapestry of the universe. Future of the Milky Way. The future evolution of the Milky Way galaxy is a topic of great interest and speculation among astronomers. One of the most significant events on the horizon is the anticipated collision with the Andromeda Galaxy. As these two massive galaxies approach each other, their gravitational forces will begin to interact, leading to a complex dance of stars and gas. This collision, expected to occur in about 4.5 billion years, will not be a catastrophic event in the traditional sense. Rather, it will result in a gradual merging process, ultimately forming a new, larger galaxy, often referred to as Milkomeda. As the Milky Way and Andromeda collide, the stars within both galaxies are unlikely to collide directly due to the vast distances between them. However, the gravitational interactions will trigger new waves of star formation and reshape the structure of both galaxies. Over billions of years, the Milky Way will evolve into a different entity, with a new arrangement of stars and possibly a new spiral structure. Ongoing research in galactic studies continues to shed light on these future scenarios. Astronomers utilize advanced telescopes and simulations to model the dynamics of galaxy interactions and the long-term evolution of galaxies. Discoveries about dark matter, star formation, and the behavior of galaxies in clusters contribute to our understanding of the Milky Way's fate. As we explore these cosmic processes, We not only gain insights into our galaxy's future, but also deepen our appreciation for the intricate and ever-changing nature of the universe. The journey of the Milky Way is far from over, and the next chapters promise to be as fascinating as its past. Terraforming. Terraforming is a fascinating concept that captures the imagination of scientists, futurists, and dreamers alike. At its core, terraforming refers to the process of modifying a planet's environment to make it more Earth-like and, ultimately, habitable for human life. This idea is particularly relevant when we consider our neighboring planets, Mars and Venus, both of which present unique challenges and opportunities for transformation. Mars, with its cold temperatures and thin atmosphere, has long been a prime candidate for terraforming. Scientists envision a future where we could warm the planet, thicken its atmosphere, and even introduce water to create a more hospitable environment. On the other hand, Venus poses a different set of challenges due to its extreme heat and dense atmosphere. However, innovative ideas such as cloud cities or reflective materials to cool the surface spark intriguing discussions about the potential for human colonization. As we delve into the possibilities of terraforming, we invite you to ponder the significance of these endeavors. What if we could establish human life beyond Earth? The implications are profound, not just for our species, but for our understanding of life itself. Join us as we explore the science, the challenges, and the dreams of making other planets our new home. The journey to terraforming could redefine our future and expand the horizons of human existence. Understanding terraforming. Terraforming is the ambitious process of altering a planet's environment to make it suitable for human habitation. The primary goal of terraforming is to create conditions that can support life, such as breathable air, stable temperatures, and liquid water. This concept is not just a science fiction fantasy. It is grounded in scientific principles that explore how we can manipulate planetary systems to achieve these goals. At the heart of terraforming are several key scientific principles, including atmospheric engineering, climate control, and ecological restoration. Atmospheric engineering involves modifying a planet's atmosphere to increase its density or change its composition, making it more similar to Earth's. For instance, on Mars, scientists propose releasing greenhouse gases to warm the planet and thicken its atmosphere, potentially allowing for liquid water to exist on the surface. Another important concept is climate control, which focuses on managing temperature and weather patterns. This could involve techniques like solar mirrors to reflect sunlight or the introduction of genetically engineered organisms that can survive in harsh conditions and help create a more balanced ecosystem. Key terms related to terraforming include biosphere, which refers to the zone of life on a planet, and terraforming agents, which are the tools or methods used to facilitate these transformations. Understanding these concepts is crucial as we explore the potential for transforming other planets into habitable environments, paving the way for humanity's future beyond Earth. Mars. The Red Planet. Mars, often referred to as the Red Planet, presents a unique set of challenges when it comes to terraforming and making it habitable for human life. Currently, Mars has a thin atmosphere composed mostly of carbon dioxide, with surface temperatures that can plummet to -80 degrees Fahrenheit. These harsh conditions, combined with high radiation levels and a lack of liquid water, make it a formidable candidate for transformation. To overcome these challenges, scientists have proposed several potential methods for warming the planet and creating a more hospitable atmosphere. One strategy involves the release of greenhouse gases, such as carbon dioxide and methane, to trap heat and raise surface temperatures. This could be achieved through industrial processes or by deploying large-scale mirrors in orbit to reflect sunlight onto the Martian surface. Another idea is to introduce genetically engineered microorganisms that could produce oxygen and contribute to a thicker atmosphere over time. Ongoing research and missions aimed at Mars exploration are crucial for understanding the planet's potential for terraforming. NASA's Perseverance rover, for example, is currently collecting samples and searching for signs of past life, while the Mars Atmosphere and Volatile Evolution MAVEN mission studies the planet's atmosphere and climate history. These efforts not only enhance our knowledge of Mars, but also lay the groundwork for future terraforming initiatives, bringing us one step closer to the dream of human life on the red planet. Venus, the hellish planet. Venus, often dubbed the hellish planet, presents some of the most extreme conditions in our solar system, making the prospect of terraforming a daunting challenge. With surface temperatures soaring around 900 degrees Fahrenheit and atmospheric pressure, 92 times that of Earth, Venus is an inhospitable environment for life as we know it. The thick atmosphere, composed mainly of carbon dioxide with clouds of sulfuric acid, creates a runaway greenhouse effect that traps heat and contributes to its hellish conditions. To transform Venus into a habitable world, scientists have proposed several theoretical approaches aimed at cooling the planet and altering its atmosphere. One idea involves deploying large-scale solar reflectors in orbit to deflect sunlight away from the planet, thereby reducing surface temperatures. Another approach suggests introducing genetically engineered microorganisms that could metabolize carbon dioxide and produce oxygen, gradually transforming the atmosphere into something more Earth-like. Additionally, creating floating cities in the upper atmosphere, where conditions are more temperate, could serve as a temporary refuge for human exploration. The implications of terraforming Venus extend beyond just making it habitable. They could revolutionize our understanding of planetary science and the limits of life. Successful terraforming efforts could pave the way for future exploration missions, offering insights into the potential for life on other planets and expanding humanity's reach in the cosmos. As we continue to study Venus, the dream of transforming this hellish world into a new home may one day become a reality. Technological innovations. As we venture into the realm of terraforming, several technological innovations are emerging that could significantly facilitate these ambitious efforts. Advancements in space technology, such as improved rocket propulsion systems and advanced materials for building habitats, are crucial for transporting equipment and personnel to other planets. For instance, reusable rockets and in-situ resource utilization (ISRU) technologies can help reduce costs and increase the feasibility of long-term missions on Mars and Venus. Artificial intelligence, AI, and robotics play a pivotal role in planetary transformation as well. AI can analyze vast amounts of data from planetary missions, helping scientists identify optimal strategies for terraforming. Robotics, on the other hand, can perform tasks in harsh environments where human presence is limited. Autonomous drones and rovers equipped with advanced sensors could monitor atmospheric changes, deploy terraforming agents, and even construct habitats, making them invaluable assets in the terraforming toolkit. Energy sources are another critical component of sustaining terraforming projects. Solar power, with its abundance in space, could provide a reliable energy source for various operations. Additionally, nuclear power offers a consistent and potent energy solution, capable of supporting large-scale terraforming efforts over extended periods. Exploring fusion energy, though still in its infancy, holds the promise of providing virtually limitless energy for future projects. Together, these technological innovations create a robust framework for terraforming efforts, pushing the boundaries of what is possible and bringing us closer to the dream of transforming other planets into habitable worlds. Ethical considerations. As we explore the concept of terraforming other planets, it is essential to address the ethical implications that accompany such monumental endeavors. Altering extraterrestrial environments raises significant moral responsibilities. Should humanity have the right to change a planet's landscape and atmosphere, potentially erasing its natural state? This question invites us to reflect on our role as stewards of not only our own planet, but also of the broader cosmos. One of the most pressing concerns is the potential impact on any existing ecosystems or life forms that may inhabit these planets, even if they are not immediately apparent. For instance, Mars and Venus may harbor microbial life or remnants of past ecosystems that could be irrevocably altered or destroyed through terraforming efforts. The ethical dilemma lies in balancing our desire to create habitable environments for humans with the responsibility to protect any forms of life that may exist, regardless of their complexity. Encouraging viewers to think critically about humanity's role in space is vital. As we venture beyond Earth, we must consider the long-term consequences of our actions. Are we prepared to face the repercussions of transforming other worlds? Engaging in discussions about the ethical dimensions of terraforming can help shape a more responsible approach to space exploration. Ultimately, as we dream of new homes among the stars, we must also commit to preserving the integrity of the universe we seek to inhabit. Future prospects. The future of terraforming and human colonization of other planets is a captivating topic that sparks both excitement and speculation. While the timeline for successful terraforming projects remains uncertain, many scientists believe that we could see initial efforts on Mars within the next few decades. With ongoing advancements in technology and a growing interest in space exploration, the feasibility of transforming Mars into a more habitable environment is becoming increasingly plausible. Projects aimed at warming the planet and creating a breathable atmosphere could begin as early as the 2030s, setting the stage for future human settlement. When it comes to Venus, the challenges are more formidable, but innovative ideas, such as floating habitats in the upper atmosphere, could pave the way for human presence. While terraforming Venus may take longer and require more advanced technologies, the potential for human settlement remains an intriguing possibility. As we continue to explore these planets, we may discover new methods and strategies that could accelerate the process. Encouraging viewers to envision a future where humanity thrives beyond Earth is essential. Imagine a world where Martian colonies flourish, with people living in biodomes, growing food, and conducting research. Picture floating cities in the clouds of Venus, where humans adapt to new ways of life. This vision of the future is not just a dream. It is a potential reality that could redefine our existence. As we embark on this journey, the possibilities for human life beyond Earth are limited only by our imagination and determination. The role of plate tectonics in shaping Earth's surface. Welcome to our exploration of one of the most fascinating processes that shape our planet: plate tectonics. At its core, plate tectonics is the scientific theory that describes the large-scale movements of Earth's lithosphere, which is divided into several tectonic plates. These plates float on the semi-fluid asthenosphere beneath them, and their interactions are responsible for many geological phenomena, including earthquakes, volcanic eruptions, and the formation of mountain ranges. Understanding plate tectonics is crucial not only for geologists, but for anyone interested in the dynamic nature of our planet. As we dive into this topic, we'll uncover how these massive plates interact at their boundaries, leading to the creation of diverse natural landscapes. From the towering peaks of the Himalayas to the deep trenches of the ocean floor, the influence of plate tectonics is evident everywhere we look. This process is not just about the Earth beneath our feet. It also plays a significant role in climate patterns, biodiversity, and even human civilization. By grasping the fundamentals of plate tectonics, we can better appreciate the beauty and complexity of Earth's surface. It helps us understand why certain areas are prone to natural disasters and how landscapes evolve over millions of years. So, whether you're a geology enthusiast or just curious about the world around you, stick around as we unravel the intricate dance of tectonic plates and their profound impact on our planet's surface. What are plate tectonics? Plate tectonics is a scientific theory that explains the structure and movement of the Earth's lithosphere, which is the rigid outer layer of our planet. This lithosphere is divided into several large and small tectonic plates that float on the semi-fluid layer of the mantle beneath them. These plates are constantly in motion, albeit very slowly, typically moving just a few centimeters each year. This movement is driven by forces such as mantle convection, slab pull, and ridge push. The boundaries where these plates meet are crucial to understanding plate tectonics. There are three main types of boundaries: divergent, convergent, and transform. At divergent boundaries, plates move apart, leading to the formation of new crust, often seen at mid-ocean ridges. Convergent boundaries occur when plates collide, resulting in one plate being forced beneath another, a process known as subduction, which can create mountain ranges and deep ocean trenches. Transform boundaries, on the other hand, involve plates sliding past each other, which can lead to earthquakes. Key concepts related to plate tectonics include continental drift and seafloor spreading. Continental drift refers to the gradual movement of continents across the Earth's surface, a theory first proposed by Alfred Wegener. Seafloor spreading describes how new oceanic crust is formed at mid-ocean ridges and pushes older crust away, contributing to the movement of tectonic plates. Together, these concepts help us understand the dynamic nature of our planet and the geological processes that shape its surface. Types of plate boundaries. Plate boundaries are the regions where tectonic plates interact, and they can be classified into three main types: divergent, convergent, and transform boundaries. Each type has distinct characteristics and geological features associated with it. Divergent boundaries occur when two tectonic plates move away from each other. This movement creates new crust as magma rises from the mantle to fill the gap. A prime example of a divergent boundary is the mid-Atlantic ridge, where the Eurasian and North American plates are pulling apart. This process not only forms new oceanic crust, but also leads to the creation of underwater volcanoes and rift valleys. Convergent boundaries, on the other hand, happen when two plates collide. This can result in one plate being forced beneath another in a process known as subduction. A well-known example is the boundary between the Indian plate and the Eurasian plate, which has led to the formation of the Himalayas. Convergent boundaries can create significant geological features such as mountain ranges, deep ocean trenches, and volcanic arcs, as the intense pressure and friction generate earthquakes and volcanic activity. Lastly, transform boundaries occur when two plates slide past each other horizontally. This lateral movement can cause stress to build up, leading to earthquakes. The San Andreas Fault in California is a classic example of a transform boundary. At these boundaries, geological features like fault lines and linear valleys can form, showcasing the dynamic nature of Earth's crust. Understanding these three types of plate boundaries is essential for grasping the processes that shape our planet's surface and influence geological events. Impact on Earth's surface. Plate tectonics plays a crucial role in shaping the Earth's surface, leading to the formation of various geological features such as mountains, valleys, and ocean basins. When tectonic plates collide at convergent boundaries, immense pressure builds up, resulting in the uplift of land and the creation of mountain ranges. The Himalayas, for instance, were formed by the collision of the Indian plate with the Eurasian plate, showcasing how powerful these tectonic forces can be. Conversely, divergent boundaries can lead to the formation of rift valleys, where land sinks as plates pull apart, creating deep valleys like the East African Rift. Ocean basins are another significant feature shaped by plate tectonics. As tectonic plates move apart at divergent boundaries, magma rises to create new oceanic crust, forming mid-ocean ridges. Over time, this process contributes to the widening of ocean basins, such as the Atlantic Ocean, which continues to expand as the Eurasian and North American plates drift apart. Tectonic activity is also responsible for earthquakes and volcanic eruptions, which are direct results of the movement and interaction of these plates. When stress builds up along fault lines at transform boundaries, it can lead to sudden releases of energy, causing earthquakes. Similarly, volcanic eruptions often occur at convergent boundaries, where subduction leads to the melting of crust and the formation of magma that can erupt through the surface. Importantly, the Earth's surface is not static. It is constantly changing due to ongoing tectonic movements. These processes shape our planet over millions of years, influencing landscapes, ecosystems, and even human settlements. Understanding the impact of plate tectonics helps us appreciate the dynamic nature of Earth and the forces that continue to mold it. Case studies. Notable examples. To truly understand the effects of plate tectonics, we can look at several notable case studies that illustrate its profound impact on our planet's geology. One of the most significant examples is the formation of the Himalayas, which arose from the collision between the Indian plate and the Eurasian plate. This monumental event began around 50 million years ago and continues today, as the plates push against each other, causing the land to uplift. The Himalayas not only boast some of the highest peaks in the world, including Mount Everest, but they also serve as a testament to the immense forces at work beneath the Earth's surface. Another compelling case study is the San Andreas Fault in California, which exemplifies a transform boundary where two tectonic plates slide past each other. This fault is notorious for its seismic activity, as the friction between the Pacific Plate and the North American Plate can lead to significant earthquakes. The San Andreas Fault has been the site of numerous tremors throughout history, highlighting the importance of understanding tectonic movements for disaster preparedness and urban planning in earthquake-prone regions. Lastly, we cannot overlook the Ring of Fire, a horseshoe-shaped zone around the edges of the Pacific Ocean known for its high volcanic activity and frequent earthquakes. This area is home to about 75% of the world's active and dormant volcanoes, including Mount St. Helens and Mount Fuji. The Ring of Fire is a direct result of tectonic plate interactions, particularly subduction zones, where oceanic plates dive beneath continental plates, leading to intense geological activity. These case studies underscore the dynamic nature of our planet and the significant role plate tectonics plays in shaping Earth's landscapes and influencing natural events. The future of plate tectonics. As we look to the future, the implications of ongoing plate tectonics for Earth are both fascinating and complex. The continuous movement of tectonic plates will undoubtedly influence not only the geological landscape, but also the climate and ecosystems. For instance, the uplift of mountain ranges can alter weather patterns, leading to changes in precipitation and temperature. This, in turn, affects local ecosystems and biodiversity. As plates shift, new habitats may emerge while others could be disrupted, prompting species to adapt, migrate, or face extinction. In the long term, the geological changes driven by plate tectonics will reshape the Earth's surface in ways we can only begin to imagine. Over millions of years, continents will continue to drift, potentially leading to the formation of new supercontinents. This process could result in significant shifts in ocean currents and climate zones, impacting global weather patterns and sea levels. Such changes could have profound effects on agriculture, water resources, and human settlements. Moreover, understanding plate tectonics is crucial for our daily lives. The knowledge of tectonic activity helps us prepare for natural disasters like earthquakes and volcanic eruptions, which can have devastating consequences. By recognizing the relevance of tectonics, we can advocate for better infrastructure, emergency preparedness, and environmental conservation. As we ponder the future of plate tectonics, it's essential to appreciate the interconnectedness of geological processes and human existence. The ongoing dance of tectonic plates will continue to shape our planet, reminding us of the dynamic nature of Earth and our place within it. Engaging with this knowledge empowers us to make informed decisions about our environment and our future. Formation of the Moon and its impact on Earth. Have you ever gazed up at the night sky and wondered about the Moon? This celestial body, glowing brightly above us, has fascinated humanity for centuries. But have you ever considered how it came to be? The formation of the Moon is a captivating story that not only explains its origins but also highlights its significant impact on our planet. The most widely accepted theory about the Moon's formation is known as the giant impact hypothesis. According to this theory, around 4.5 billion years ago, a Mars-sized body, often referred to as Theia, collided with the early Earth. This colossal impact ejected a massive amount of debris into orbit around our planet. Over time, this debris coalesced to form the Moon. This dramatic event not only shaped our lunar companion, but also played a crucial role in the development of Earth itself. But why should we care about how the Moon was formed? The Moon is more than just a beautiful sight in the sky. It has a profound influence on Earth. Its gravitational pull is responsible for the ocean tides, which are essential for marine life and coastal ecosystems. The Moon also stabilizes Earth's axial tilt, which helps maintain a relatively stable climate over geological timescales. Without the Moon, our planet could have experienced extreme climate fluctuations, making it less hospitable for life as we know it. As we dive deeper into this topic, we'll explore not only the fascinating science behind the Moon's formation, but also its ongoing impact on Earth. From its role in shaping our oceans to its influence on our cultural narratives, the Moon is a vital part of our existence. So, stick around as we unravel the mysteries of our closest celestial neighbor and discover how it continues to shape our world today. Theories of Moon formation. When it comes to understanding how the Moon was formed, scientists have proposed several intriguing theories, each offering a unique perspective on this celestial mystery. The most widely accepted explanation is the giant impact hypothesis. According to this theory, the Moon was created from the debris resulting from a colossal collision between the early Earth and a Mars-sized body known as Theia. This cataclysmic event occurred approximately 4.5 billion years ago, sending a significant amount of material into orbit around Earth. Over time, this debris coalesced to form the Moon we see today. The implications of the giant impact hypothesis are profound. Not only does it explain the Moon's composition, which is strikingly similar to Earth's outer layers, but it also suggests that the Moon's formation played a crucial role in stabilizing Earth's axial tilt. This stability has allowed for a relatively consistent climate, fostering the development of life. However, the giant impact hypothesis is not the only theory on the table. Another notable explanation is the double planet hypothesis, which posits that the Earth and Moon formed together as a double system from the primordial accretion disk of the Sun. While this theory accounts for some similarities between the Earth and Moon, it struggles to explain the differences in their compositions, particularly the Moon's lack of volatile elements. Scientific evidence supporting these theories comes from various sources, including lunar rock samples brought back by the Apollo missions. These samples reveal isotopic similarities between Earth and Moon rocks, lending credence to the giant impact hypothesis. Additionally, computer simulations of planetary formation have shown that such a massive collision could indeed produce a moon-like body. As we explore these theories further, we gain a deeper understanding of not just the Moon's origins, but also its lasting impact on our planet. Each theory adds a layer of complexity to our knowledge, inviting us to ponder the intricate dance between Earth and its celestial companion. Geological features of the Moon. The Moon's surface is a fascinating tapestry of geological features that tell the story of its tumultuous history. As we explore this celestial body, we encounter a variety of landscapes, including craters, maria, and highlands, each revealing clues about the Moon's formation and evolution. One of the most prominent features of the Moon's surface is its craters. These impact scars, created by collisions with asteroids and comets, vary in size from small pockmarks to massive basins. The largest of these, such as the Imbrium and Serenitatis basins, were formed during the Moon's early history, when it was bombarded by debris left over from the formation of the solar system. The craters are often surrounded by rays of ejecta, which are materials blasted out during the impact, showcasing the violent history of the Moon. In contrast to the heavily cratered regions, the Moon also features vast, dark plains known as maria. These basaltic plains were formed by ancient volcanic activity, which filled in the basins created by impacts. The maria are less cratered than the highlands, indicating that they are younger and were formed after the initial bombardment phase. The most famous maria, such as Mare Tranquillitatis and Mare Imbrium, are visible from Earth and have been the subject of much fascination. The highlands, on the other hand, are the Moon's oldest regions, characterized by rugged terrain and a higher density of craters. These areas represent the original crust of the Moon, formed during its early cooling period. The contrast between the highlands and maria provides insight into the Moon's geological history, illustrating how it transitioned from a heavily bombarded surface to one that experienced volcanic activity. Understanding these geological features not only enhances our appreciation of the Moon's beauty, but also connects us to its formation history. Each crater, plain, and highland is a testament to the dynamic processes that have shaped our closest celestial neighbor over billions of years. As we continue to study the Moon, we uncover more about its past and, in turn, our own planet's history. The Moon's influence on Earth. The Moon is not just a beautiful sight in our night sky. It plays a crucial role in shaping various aspects of life on Earth. One of its most significant influences is the creation of tides. The gravitational pull of the Moon causes the oceans to bulge, resulting in high and low tides. This tidal movement is essential for marine ecosystems, as it helps to circulate nutrients and supports diverse marine life. Tides also play a vital role in coastal environments, influencing the behavior of organisms and the health of habitats such as estuaries and mangroves. Beyond tides, the Moon has a profound impact on Earth's axial tilt, which is the angle at which our planet rotates. This tilt is responsible for the changing seasons and contributes to climate stability. The Moon's gravitational influence helps to stabilize Earth's axial tilt over long periods, preventing extreme variations that could lead to drastic climate changes. Without the Moon, our planet might experience significant fluctuations in climate, making it less hospitable for life as we know it. The Moon's influence extends beyond the physical realm. It has also held immense cultural and historical significance throughout human history. Many ancient civilizations revered the Moon, associating it with various deities and using its phases to mark time. From calendars to agricultural practices, the lunar cycle has guided human activities for millennia. The moon has inspired countless myths, art, and literature, symbolizing everything from romance to mystery. As we examine the moon's multifaceted influence on Earth, we gain a deeper appreciation for its role in our lives. From the rhythmic ebb and flow of the tides to the stability of our climate and the rich tapestry of cultural significance, the moon is an integral part of our planet's story. Understanding these connections not only enhances our knowledge of the moon, but also deepens our connection to the world around us. Future exploration of the moon. As we look to the future, lunar exploration is entering an exciting new era, marked by ambitious missions and international collaborations. One of the most significant initiatives is NASA's Artemis program, which aims to return humans to the moon by the mid-2020s. The primary goal of Artemis is to land the first woman and the next man on the lunar surface, specifically at the lunar South Pole, a region rich in resources and scientific potential. This program not only seeks to advance our understanding of the moon, but also serves as a stepping stone for future crewed missions to Mars. Artemis is not a solo endeavor. It emphasizes international partnerships and collaboration. NASA is working alongside space agencies from around the world, including the European Space Agency, ESA, the Japan Aerospace Exploration Agency, JAXA, and the Canadian Space Agency, CSA. These collaborations aim to share knowledge, technology, and resources, enhancing the overall success of lunar exploration. The Artemis program also includes the Lunar Gateway, a space station that will orbit the moon and serve as a hub for lunar missions, facilitating research and exploration. Looking further ahead, the potential for human colonization of the moon is becoming increasingly feasible. Scientists and engineers are exploring the idea of establishing sustainable habitats on the lunar surface. These habitats could support long-term human presence, enabling research and exploration beyond short missions. Additionally, the moon is believed to harbor valuable resources, such as water ice, which could be utilized for life support and fuel production. This resource utilization could significantly reduce the costs and logistical challenges of deep space exploration. As we embark on this new chapter of lunar exploration, the moon stands as a beacon of opportunity. With programs like Artemis and international collaborations paving the way, we are on the brink of unlocking the moon's secrets and harnessing its resources. The future of lunar exploration promises not only to expand our scientific knowledge, but also to inspire generations to come. The evolution of plants and the greening of Earth. Welcome to our exploration of the fascinating evolution of plants and the greening of Earth. Plants are not just a backdrop to our planet. They are the very foundation of life as we know it. From the tiniest moss to the towering redwoods, the diversity of plant life is a testament to millions of years of evolution. Understanding how plants have evolved is crucial because they play a pivotal role in shaping ecosystems, influencing climate, and supporting countless species, including humans. Imagine a world without plants, no lush forests, no vibrant flowers, and no fresh air. The significance of plant evolution in Earth's history cannot be overstated. It marks the transition from barren landscapes to thriving ecosystems, transforming our planet into a green oasis. This greening process has not only provided habitats for countless organisms, but has also been instrumental in regulating the atmosphere and cycling nutrients. As we delve deeper into this topic, we'll uncover the incredible adaptations that have allowed plants to thrive in diverse environments, from arid deserts to lush rainforests. By understanding the evolutionary journey of plants, we gain insight into their vital role in maintaining ecological balance. So, join us as we embark on this botanical adventure, celebrating the remarkable diversity of plant life and its profound impact on our world. The origin of plants. To understand the origins of plants, we must journey back over 500 million years to a time when life was predominantly aquatic. The earliest forms of plant life were simple algae, thriving in the oceans. These microscopic organisms laid the groundwork for the incredible diversity of plant life we see today. The transition from aquatic algae to terrestrial plants was a monumental leap in evolution, driven by the need to adapt to life on land. One of the key factors in this transition was the development of photosynthesis. This remarkable process allowed early plants to harness sunlight, converting carbon dioxide and water into energy and oxygen. As these primitive plants began to colonize land, they not only provided a new source of food for emerging terrestrial organisms, but also played a crucial role in shaping the atmosphere. The oxygen produced through photosynthesis contributed to the gradual transformation of Earth's environment, making it more hospitable for life. Fossil evidence provides a fascinating glimpse into this evolutionary journey. Fossils of ancient plants, such as the liverworts and mosses, reveal how these early life forms adapted to terrestrial conditions. The discovery of fossils like Cooksonia, one of the first vascular plants, showcases the innovations that allowed plants to thrive on land. By studying these remnants of the past, we gain valuable insights into how plants evolved and diversified, setting the stage for the rich tapestry of life we enjoy today. The age of ferns and gymnosperms. During the Mesozoic era, approximately 252 to 66 million years ago, ferns and gymnosperms emerged as the dominant plant groups, shaping the landscapes of ancient Earth. Ferns, with their lush fronds and ability to thrive in diverse environments, adapted well to the humid conditions of this era. Their reproductive strategy, relying on spores rather than seeds, allowed them to colonize a variety of habitats, from dense forests to open woodlands. Gymnosperms, on the other hand, introduced a revolutionary advancement in plant evolution: seeds. This adaptation provided them with a significant advantage, enabling them to reproduce more efficiently and survive in drier conditions. With their needle-like leaves and thick bark, gymnosperms, like conifers, were well suited to withstand harsh climates, making them key players in many ancient ecosystems. The ecological roles of ferns and gymnosperms during the Mesozoic were vital. They provided essential habitats and food sources for a myriad of organisms, including the dinosaurs that roamed the Earth. These plants contributed to the stabilization of soils and the cycling of nutrients, fostering rich biodiversity. Significant fossil records, such as those found in the famous Jurassic deposits, showcase the incredible diversity of ferns and gymnosperms. Fossils of giant cycads and towering conifers reveal a world teeming with life and complexity. By examining these ancient remains, we gain a deeper appreciation for the evolutionary journey of plants and their enduring impact on Earth's ecosystems. The rise of angiosperms. The emergence of angiosperms, or flowering plants, marked a significant turning point in the history of plant evolution. Appearing around 140 million years ago, angiosperms quickly diversified and became the dominant group of plants on Earth. One of the key advantages of flowering plants over their gymnosperm counterparts is their ability to produce flowers and fruits, which facilitate more efficient reproduction. The enclosed seeds within fruits provide better protection and nourishment, enhancing the survival rates of the next generation. A remarkable aspect of angiosperm evolution is their co-evolution with pollinators. As flowering plants developed colorful blooms and enticing scents, they attracted a variety of pollinators, including bees, butterflies, and birds. This mutualistic relationship not only ensured the successful transfer of pollen, but also allowed for greater genetic diversity among plant populations. The intricate adaptations seen in both angiosperms and their pollinators highlight the dynamic interplay of evolution in shaping ecosystems. The diversity of angiosperm species is astounding, with examples ranging from the delicate orchids of tropical rainforests to the sturdy oak trees of temperate woodlands. Each species has adapted to its specific habitat, showcasing a wide array of forms, colors, and functions. For instance, water lilies thrive in aquatic environments, while cacti have evolved to survive in arid deserts. This incredible variety underscores the importance of angiosperms in maintaining ecological balance and supporting a vast array of life forms across the globe. The impact of plants on climate. Plants have played a crucial role in shaping Earth's climate over geological time, acting as vital components of the planet's ecological balance. One of the most significant contributions of plants is their ability to sequester carbon dioxide from the atmosphere through the process of photosynthesis. By absorbing CO2, plants help mitigate the greenhouse effect, reducing the impact of climate change. Additionally, as they produce oxygen as a byproduct, plants have been essential in creating and maintaining the breathable atmosphere that supports life. Vegetation also significantly influences weather patterns and soil health. Dense plant cover can alter local climates by affecting humidity and temperature, leading to increased rainfall in certain areas. This, in turn, promotes healthy soil by preventing erosion and enhancing nutrient cycling. Healthy soils, rich in organic matter, support diverse plant life and contribute to the overall resilience of ecosystems. Forests, in particular, are critical in regulating global temperatures. They act as carbon sinks, storing vast amounts of carbon and helping to cool the planet. The loss of forests through deforestation not only releases stored carbon back into the atmosphere, but also diminishes the planet's capacity to absorb CO2, exacerbating climate change. Furthermore, forests provide essential habitats for countless species, maintain biodiversity, and play a key role in the water cycle. Understanding the impact of plants on climate is vital for developing strategies to combat climate change and protect our planet's future. Human interaction with plants. The relationship between humans and plant life has evolved dramatically throughout history, shaping civilizations and cultures around the globe. One of the most significant developments was the domestication of plants, which began around 10,000 years ago. Early humans transitioned from foraging to agriculture, cultivating crops such as wheat, rice, and maize. This shift not only provided a stable food supply, but also led to the rise of settled communities and the development of complex societies. Agricultural practices have since evolved, incorporating techniques like crop rotation and selective breeding to enhance yields and resilience. Plants also hold deep cultural significance in various societies. They are often intertwined with traditions, rituals, and identities. For instance, in many indigenous cultures, certain plants are revered for their medicinal properties or spiritual importance. Festivals celebrating harvests and the changing seasons highlight the vital role plants play in human life, symbolizing sustenance and connection to the earth. However, the impact of human activity on plant life has not always been positive. Deforestation for agriculture, urbanization, and industrialization has led to significant habitat loss and biodiversity decline. This destruction not only threatens plant species, but also disrupts ecosystems and contributes to climate change. In response, conservation efforts have gained momentum, focusing on sustainable practices, reforestation, and the protection of endangered species. By recognizing the importance of plants in our history and future, we can foster a more harmonious relationship with the natural world. ensuring the survival of both plants and humanity. Future of plant evolution. As we look to the future, the trajectory of plant evolution is poised to be significantly influenced by changing environments, particularly due to climate change. Rising temperatures, shifting precipitation patterns, and increased frequency of extreme weather events pose serious challenges for many plant species. Some may struggle to adapt quickly enough, leading to shifts in biodiversity and the potential extinction of vulnerable species. However, others may thrive, evolving new traits that allow them to survive in harsher conditions, ultimately reshaping ecosystems. Ongoing research in plant genetics and biotechnology offers promising avenues for understanding and enhancing plant resilience. Scientists are exploring genetic modifications and selective breeding techniques to develop crops that can withstand drought, pests, and diseases. This research not only aims to secure food supplies, but also seeks to bolster the natural resilience of wild plant populations, ensuring they can adapt to rapidly changing climates. As we navigate these challenges, it is crucial for individuals to consider their role in plant conservation. Simple actions, such as supporting sustainable agriculture, participating in reforestation efforts, and advocating for policies that protect natural habitats, can make a significant difference. By fostering a deeper appreciation for plant life and its importance to our ecosystems, we can contribute to a future where both plants and humans thrive together. The evolution of plants is not just a scientific concern, it is a shared responsibility that requires collective action and awareness in the face of environmental change, the ice ages, and their effect on Earth's evolution. Introduction. The Ice Ages are a captivating chapter in Earth's history, marking periods of dramatic climate change that have profoundly influenced the planet's evolution. These frigid epochs, characterized by extensive glaciation, not only sculpted our landscapes, but also played a pivotal role in shaping the biodiversity we see today. Imagine vast ice sheets stretching across continents, transforming lush forests into barren tundras, and altering the course of rivers. This interplay between climate and evolution is nothing short of fascinating. During these icy periods, species were forced to adapt, migrate, or face extinction. The harsh conditions led to the emergence of resilient life forms, while others vanished, leaving behind a rich tapestry of evolutionary stories. For instance, the Ice Ages contributed to the development of large mammals, like woolly mammoths and saber-toothed cats, which roamed the frozen landscapes. As the climate warmed and the ice retreated, new ecosystems flourished, paving the way for the diverse array of species we have today. In this video, we will delve into the significance of the Ice Ages, exploring how they not only shaped the physical world, but also influenced the very fabric of life on Earth. From the dramatic shifts in biodiversity to the stunning transformations of our planet's landscapes, the Ice Ages offer a thrilling glimpse into the dynamic relationship between climate and evolution. Join us as we uncover the secrets of these icy epochs and their lasting impact on our world. What are Ice Ages? Ice ages are prolonged periods in Earth's history characterized by significant drops in global temperatures, leading to the expansion of ice sheets and glaciers across large portions of the planet. These epochs are marked by alternating glacial and interglacial periods. During glacial periods, vast ice sheets cover regions like North America and Europe, while interglacial periods see a retreat of ice, allowing ecosystems to flourish and temperatures to rise. This cyclical nature of ice ages is crucial for understanding Earth's climatic history. Scientists identify ice ages using a combination of geological and paleoclimatic evidence. Key indicators include the presence of glacial deposits, changes in sea levels, and variations in oxygen isotopes found in ice cores and sediment layers. These criteria help researchers pinpoint when significant cooling events occurred and how long they lasted. Ice ages play a vital role in influencing global climate patterns. They affect ocean currents, atmospheric circulation, and even the distribution of flora and fauna. The cooling associated with ice ages can lead to shifts in weather patterns, impacting everything from rainfall to temperature extremes. Moreover, the interplay between ice ages and greenhouse gas concentrations highlights the delicate balance of Earth's climate system. Understanding ice ages not only sheds light on past climate changes, but also provides valuable insights into potential future shifts in our planet's climate. The timeline of ice ages. Throughout Earth's history, several significant ice ages have shaped the planet's geological features and influenced the evolution of life. The most notable of these is the Pleistocene Ice Age, which began around 2.6 million years ago and lasted until approximately 11,700 years ago. This period is characterized by repeated glacial cycles where massive ice sheets advanced and retreated across North America, Europe, and Asia. The Pleistocene is marked by key events such as the last glacial maximum around 20,000 years ago, when ice covered much of Canada and the northern United States, dramatically altering landscapes and ecosystems. Before the Pleistocene, the Earth experienced the Karoo Ice Age, which occurred roughly 360 to 260 million years ago during the late Paleozoic era. This ice age was significant for the formation of glacial deposits in what is now Africa, South America, and Australia, contributing to the supercontinent Gondwana's geological history. Another important ice age was the Andean-Saharan Ice Age, which took place around 450 to 420 million years ago. This period saw glaciation in the southern hemisphere, particularly in the Andes and parts of Africa, leaving behind distinctive geological features such as striations and moraines. Each of these ice ages has left an indelible mark on Earth's surface, sculpting valleys, shaping coastlines, and influencing the distribution of flora and fauna. Understanding this timeline helps us appreciate the dynamic nature of our planet and the profound impact of climate on geological evolution. Effects on climate and environment. Ice ages have had profound effects on Earth's climate and environment, primarily characterized by significant cooling and warming trends. During glacial periods, global temperatures plummeted, leading to the expansion of ice sheets and glaciers. This cooling not only transformed landscapes, but also altered weather patterns, resulting in harsher conditions for many species. Conversely, during interglacial periods, temperatures rose, causing glaciers to retreat and ecosystems to thrive, creating a dynamic cycle of climate change that has shaped life on Earth. The movement of glaciers during ice ages played a crucial role in reshaping landscapes and ecosystems. As glaciers advanced, they carved out valleys, created fjords, and deposited sediments, forming features like moraines and drumlins. This glacial activity not only sculpted the physical geography of regions, but also influenced the distribution of plant and animal species, leading to the development of unique ecosystems adapted to changing conditions. Ice ages also had a significant impact on sea levels and ocean currents. During glacial periods, vast amounts of water were trapped in ice sheets, causing sea levels to drop significantly. This drop exposed continental shelves and altered coastlines, while the redistribution of water affected ocean currents. Changes in ocean circulation patterns influenced global climate, impacting weather systems and marine ecosystems. Understanding these effects helps us appreciate the intricate connections between ice ages, climate, and the environment, revealing how past events continue to shape our planet today. Impact on biodiversity. Ice ages have played a crucial role in influencing the evolution of species, acting as both a catalyst for extinction and a driver of adaptation. During these frigid periods, many species faced harsh conditions that led to significant population declines and, in some cases, extinction. For instance, large mammals like the woolly mammoth and the saber-toothed cat struggled to survive as their habitats changed and food sources dwindled. However, not all species succumbed to these challenges. Some adapted remarkably well to the shifting climates. Examples of species that thrived during ice ages include the reindeer and the Arctic fox, both of which developed specialized adaptations to cope with extreme cold and scarce resources. These species evolved traits such as thicker fur and behavioral changes that allowed them to migrate in search of food, showcasing the resilience of life in the face of adversity. The impact of ice ages on biodiversity extends beyond individual species. These climatic shifts have shaped modern ecosystems and the distribution of species we see today. The genetic diversity that emerged during these periods has contributed to the resilience of many species, allowing them to adapt to current environmental changes. Furthermore, the isolation of populations due to glaciation led to speciation events, resulting in the rich tapestry of life we observe in various habitats around the world. By understanding the influence of ice ages on evolution, we gain valuable insights into the complex interplay between climate and biodiversity throughout Earth's history. Human evolution and ice ages. The relationship between ice ages and human evolution is a fascinating interplay that significantly influenced early human migration patterns and societal development. As ice ages transformed the Earth's climate, they created both barriers and pathways for human populations. During glacial periods, lower sea levels exposed land bridges, such as the Bering Land Bridge, allowing early humans to migrate from Asia to North America. This movement facilitated the spread of human populations across vast regions, leading to the colonization of new territories. However, the challenges posed by ice ages were immense. Early humans faced extreme cold, scarce resources, and shifting ecosystems that required them to adapt quickly. These challenges spurred innovations in tool-making, clothing, and shelter construction as humans developed strategies to survive in harsh environments. For instance, the use of fire became crucial for warmth and cooking, while the development of specialized hunting tools allowed for more effective hunting of large mammals. The influence of climate on the development of human societies cannot be overstated. As ice ages ended and climates warmed, new ecosystems emerged, providing abundant resources that supported larger populations and the establishment of more complex societies. The transition from nomadic lifestyles to settled communities was facilitated by the availability of food and favorable living conditions. Understanding the impact of ice ages on human evolution highlights the resilience and adaptability of our species in the face of environmental challenges, shaping the trajectory of human history. Modern implications of ice ages. The relevance of ice ages to current climate change discussions is profound, as studying these past events can provide critical insights into our understanding of contemporary climate trends. By examining the patterns of temperature fluctuations, glacial advances, and retreats during previous ice ages, scientists can better predict how current climate change may unfold. For instance, the relationship between greenhouse gas concentrations and global temperatures observed during ice ages helps us comprehend the potential consequences of rising carbon levels today. As we face the reality of climate change, the potential future impacts on glacial regions are alarming. Many glaciers around the world are retreating at unprecedented rates, leading to rising sea levels and altered freshwater supplies. This not only threatens coastal communities, but also disrupts ecosystems that depend on glacial meltwater. The loss of ice cover can further accelerate warming, as less sunlight is reflected away from the Earth's surface, creating a feedback loop that exacerbates climate change. Preserving Ice Age remnants, such as glacial deposits and ancient ice cores, is crucial for scientific research. These remnants serve as valuable records of Earth's climatic history, offering insights into past ecosystems and species adaptations. By studying these remnants, researchers can gain a deeper understanding of how life on Earth has responded to climate shifts, informing conservation efforts and strategies to mitigate the impacts of current climate change. Ultimately, the lessons learned from ice ages are essential for navigating the challenges of our rapidly changing world. The formation and evolution of black holes. Welcome to our deep dive into one of the universe's most fascinating phenomena: black holes. In this video, we'll explore the formation and evolution of these enigmatic cosmic giants, unraveling the mysteries that surround them. Have you ever gazed up at the night sky and wondered what lies beyond the twinkling stars? Black holes are not just the stuff of science fiction. They play a crucial role in the fabric of our universe. We'll start by discussing how black holes are formed, beginning with the life cycle of massive stars. You'll learn about the dramatic events that lead to a star's collapse and the birth of a black hole. From there, we'll delve into the different types of black holes, including stellar, supermassive, and even primordial black holes, each with its own unique characteristics and significance. But why should we care about black holes? These cosmic entities are not just voids in space. They are key players in the evolution of galaxies and the dynamics of the universe. Their gravitational pull influences the orbits of stars and can even affect the formation of new celestial bodies. Throughout this video, we aim to engage your curiosity and provide you with a deeper understanding of black holes. By the end, you'll appreciate their importance in the cosmos and perhaps even feel inspired to explore the mysteries of the universe further. So, buckle up as we embark on this cosmic journey into the heart of black holes. What are black holes? Black holes are one of the most intriguing and mysterious objects in the universe. At their core, they are regions in space where the gravitational pull is so strong that nothing, not even light, can escape from them. This phenomenon occurs when a massive star exhausts its nuclear fuel and collapses under its own gravity, leading to the formation of a black hole. The boundary surrounding a black hole is known as the event horizon. This is the point of no return. Once anything crosses this threshold, it is inexorably drawn into the black hole and cannot escape. Inside the event horizon lies the singularity, a point where the gravitational forces are thought to be infinitely strong, and the laws of physics as we know them cease to function. Black holes come in various types, each defined by their mass and formation process. The most common type is the stellar black hole, which forms from the remnants of a massive star after a supernova explosion. These black holes typically have a mass ranging from about 3 to several tens of solar masses. Next, we have supermassive black holes, which can be millions to billions of times more massive than our Sun. These giants are often found at the centers of galaxies, including our own Milky Way, and their formation is still a subject of research. Lastly, there are intermediate black holes, which fall between stellar and supermassive black holes in terms of mass. Their existence hints at a complex evolutionary process that scientists are eager to understand. Together, these types of black holes contribute to the rich tapestry of our universe, making them a captivating subject of study. The formation of black holes. The formation of black holes is a fascinating process that begins with the life cycle of massive stars. These stars, which are at least 8 times more massive than our Sun, go through a series of stages during their existence. Initially, They fuse hydrogen into helium in their cores, generating immense energy that counteracts the force of gravity. However, as they exhaust their hydrogen fuel, they begin to fuse heavier elements, leading to the creation of iron in their cores. Once a massive star forms an iron core, it can no longer sustain nuclear fusion. The core becomes unstable and collapses under its own gravity, leading to a dramatic event known as a supernova. This explosion is one of the most energetic events in the universe, blasting away the outer layers of the star and leaving behind a dense remnant. If the remaining core has enough mass, typically more than 3 solar masses, it will continue to collapse, ultimately forming a black hole. For a black hole to form, certain conditions must be met. The star must be sufficiently massive to undergo the gravitational collapse after the supernova. Additionally, the environment surrounding the star can influence the process. For instance, if the star is in a binary system, interactions with a companion star can affect its mass and the dynamics of the collapse. Understanding these processes not only sheds light on how black holes are created, but also highlights their significance in the evolution of galaxies and the universe itself. Each black hole formed is a testament to the life cycle of stars and the intricate dance of cosmic forces at play. The evolution of black holes. Once formed, black holes continue to evolve over time, primarily through the process of accretion. This occurs when a black hole pulls in surrounding matter, such as gas, dust, and even stars. As this material spirals into the black hole, it forms an accretion disk, heating up and emitting intense radiation, often making the black hole visible to astronomers. This process allows black holes to grow significantly in mass, sometimes leading to the formation of supermassive black holes at the centers of galaxies. Another fascinating aspect of black hole evolution is the merging of black holes. When two black holes come close enough, they can spiral toward each other due to gravitational attraction. Eventually, they may collide and merge into a single, larger black hole. This event releases an enormous amount of energy, often detectable as gravitational waves. The study of these mergers not only helps us understand the dynamics of black holes, but also provides insights into the formation and evolution of galaxies. Black holes also have profound effects on their surrounding environments. Their immense gravitational pull can influence the orbits of nearby stars and gas clouds, shaping the structure of galaxies. In some cases, the energy emitted during accretion can drive powerful jets of particles away from the black hole, impacting star formation in the surrounding region. Overall, the evolution of black holes is a dynamic process that plays a crucial role in the cosmic landscape. By studying these changes, we gain a deeper understanding of the universe's history and the intricate relationships between black holes, stars, and galaxies. Black holes and the universe. Black holes play a pivotal role in shaping the cosmos, influencing everything from galaxy formation to our understanding of fundamental physics. One of the most significant impacts of black holes is their role in the formation and evolution of galaxies. Supermassive black holes, often found at the centers of galaxies, exert a powerful gravitational pull that can affect the motion of stars and gas within the galaxy. This interaction can regulate star formation rates and help determine the overall structure of the galaxy. In essence, black holes act as anchors around which galaxies can form and evolve. Another fascinating aspect of black holes is the phenomenon of gravitational waves, which are ripples in space-time caused by the acceleration of massive objects. When two black holes merge, they create a significant disturbance in the fabric of space-time, generating gravitational waves that can be detected by observatories like LIGO and Virgo. These observations not only confirm predictions made by Einstein's general theory of relativity, but also provide valuable insights into the properties of black holes, such as their masses and spins. The study of gravitational waves opens a new window into the universe, allowing us to observe cosmic events that were previously hidden from view. Moreover, black holes are essential for advancing our understanding of fundamental physics. They challenge our current theories and push the boundaries of what we know about gravity, quantum mechanics, and the nature of space-time. By studying black holes, scientists hope to uncover new principles that govern the universe, potentially leading to a unified theory that bridges the gap between general relativity and quantum physics. In this way, black holes are not just cosmic curiosities. They are key to unlocking the mysteries of the universe itself. Current research and discoveries. Recent advancements in black hole research have significantly enhanced our understanding of these enigmatic cosmic entities. One of the most groundbreaking developments has been the work of the Event Horizon Telescope, EHT, a global network of radio telescopes that captured the first-ever image of a black hole's event horizon in 2019. This historic image, depicting the supermassive black hole at the center of the galaxy M87, provided direct visual evidence of black holes and confirmed many theoretical predictions. The EHT's work continues, with ongoing efforts to refine imaging techniques and study other black holes, including the one at the center of our Milky Way, known as Sagittarius, a star. In addition to imaging black holes, researchers have made significant strides in understanding black hole mergers and the gravitational waves they produce. The detection of gravitational waves from merging black holes has opened a new frontier in astrophysics. Since the first detection by LIGO in 2015, multiple events have been observed, allowing scientists to study the properties of black holes, such as their masses and spins. These discoveries have not only confirmed aspects of general relativity, but have also provided insights into the population and formation mechanisms of black holes in the universe. Looking ahead, ongoing research and future missions are set to further unravel the mysteries of black holes. Projects like the Laser Interferometer Space Antenna, LISA, aim to detect gravitational waves from a broader range of sources, including supermassive black hole mergers. Additionally, advancements in observational technology and theoretical models promise to deepen our understanding of black holes and their role in the cosmos. As we continue to explore these fascinating objects, the potential for new discoveries remains vast, promising to reshape our understanding of the universe. The search for extraterrestrial life and exoplanets. The search for extraterrestrial life and exoplanets is one of the most captivating endeavors in modern science. As we gaze into the vastness of the universe, the question of whether we are alone becomes increasingly significant. Discovering life beyond Earth could not only redefine our understanding of biology, but also reshape our philosophical perspectives on existence. The implications of finding extraterrestrial life are profound, potentially offering insights into the origins of life itself and our place in the cosmos. Recent advancements in technology have revolutionized our ability to explore distant worlds. Telescopes, like the James Webb Space Telescope, and missions such as Kepler have enabled scientists to detect thousands of exoplanets, some of which reside in the habitable zones of their stars. These technological breakthroughs allow us to analyze the atmospheres of these planets, searching for biosignatures that could indicate the presence of life. As we delve into the mysteries of the universe, we are reminded of our own insignificance in the grand scheme of things. Each discovery brings us closer to understanding not just the cosmos, but also our role within it. Join us as we explore the exciting possibilities that lie beyond our planet. The importance of extraterrestrial life. The search for extraterrestrial life is not just a scientific curiosity. It holds profound implications for humanity. Discovering life beyond Earth would fundamentally alter our understanding of biology and evolution. It could reveal that life can arise in diverse environments, challenging our current definitions and theories about how life develops. This knowledge could lead to new insights into the resilience of life and its potential to adapt, reshaping our understanding of evolution itself. Moreover, the implications extend beyond biology. The discovery of extraterrestrial life could foster a sense of unity among humanity, reminding us that we are part of a larger cosmic community. This realization might inspire collaborative efforts in science and technology as nations come together to explore the universe and share knowledge. Additionally, the technological advancements that could arise from this search are immense. The tools and techniques developed for detecting and studying exoplanets often lead to innovations in other fields, such as materials, science, robotics, and data analysis. These advancements could enhance our daily lives, improving everything from healthcare to environmental sustainability. Ultimately, the quest for extraterrestrial life is a journey that could redefine our existence and propel humanity into a new era of discovery and understanding. What are exoplanets? Exoplanets, or extrasolar planets, are celestial bodies that orbit stars outside our solar system. They come in various sizes and compositions, ranging from gas giants like Jupiter to rocky planets similar to Earth. Identifying these distant worlds involves advanced techniques such as the transit method, where astronomers observe the dimming of a star's light as a planet passes in front of it, and the radial velocity method, which detects wobbles in a star's motion caused by gravitational pulls from orbiting planets. Exoplanets can be categorized into several types, including terrestrial planets, which are rocky and potentially habitable, and gas giants, which are often inhospitable due to their extreme atmospheres. Some exoplanets are located in the Goldilocks zone, the region around a star, where conditions might be just right for liquid water to exist, an essential ingredient for life as we know it. Studying exoplanets is crucial in the search for extraterrestrial life, as it allows scientists to assess their habitability. By analyzing their atmospheres and surface conditions, researchers can identify potential biosignatures or signs of life. This exploration not only enhances our understanding of the universe, but also brings us closer to answering the age-old question: are we alone? Methods of detection. Detecting exoplanets requires innovative techniques, each with its unique strengths and challenges. One of the most widely used methods is the transit method. This technique involves monitoring the brightness of a star over time. When a planet passes in front of its host star, it causes a temporary dip in the star's brightness. By analyzing these dips, astronomers can determine the planet's size and orbital period, providing valuable insights into its potential habitability. Another important method is radial velocity, also known as the Doppler method. This technique measures the star's wobble caused by the gravitational pull of an orbiting planet. As the planet orbits, it causes the star to move slightly toward and away from us, leading to shifts in the star's spectral lines. By analyzing these shifts, scientists can calculate the planet's mass and infer its composition, helping to distinguish between gas giants and rocky planets. Direct imaging is another method that aims to capture images of exoplanets by blocking out the star's light. While this approach can provide detailed information about a planet's atmosphere and surface, it is challenging due to the vast distances and brightness of stars. Despite these difficulties, advancements in technology continue to improve our ability to observe these distant worlds. The habitable zone. The habitable zone, often referred to as the Goldilocks zone, is the region around a star, where conditions are just right for liquid water to exist on a planet's surface. This zone is crucial for the potential development of life as we know it. as water is a fundamental ingredient for biological processes. The distance from the star determines the temperature of the planet, making the habitable zone a key focus in the search for extraterrestrial life. Several factors contribute to a planet's habitability beyond its location in the habitable zone. These include the planet's atmosphere, which can regulate temperature and protect against harmful radiation, as well as its geological activity, which can recycle nutrients essential for life. The presence of a magnetic field is also important, as it shields the planet from solar winds that could strip away the atmosphere. Examples of exoplanets located within their star's habitable zone include Kepler 186f, a rocky planet that orbits a star similar to our Sun, and Proxima Centauri b, which is the closest known exoplanet to Earth. These discoveries fuel our hopes of finding life beyond our planet and deepen our understanding of where life might thrive in the universe. Recent discoveries. In recent years, the search for extraterrestrial life has yielded exciting discoveries that expand our understanding of the universe. Notable exoplanets such as TOI 700DE, discovered by NASA's Transiting Exoplanet Survey Satellite, TESS, have captured attention due to their location within the habitable zone of their star. This Earth-sized planet offers a promising environment for potential life, sparking interest in further studies. The Kepler Space Telescope has also played a pivotal role in these discoveries. Over its mission, Kepler identified thousands of exoplanets, including many inhabitable zones, such as Kepler 452b, often dubbed Earth's cousin. These findings have provided invaluable data on the diversity of planetary systems and the potential for life beyond our own. The significance of these discoveries extends beyond individual planets. They contribute to a broader understanding of how common habitable conditions might be in the universe. Each new exoplanet found in a habitable zone raises the possibility that life could exist elsewhere, prompting further exploration and research. As technology advances and missions like TESS continue to operate, the quest for extraterrestrial life becomes increasingly promising, bringing us closer to answering one of humanity's most profound questions. The search for biosignatures. Biosignatures are indicators of past or present life, and they play a crucial role in the field of astrobiology. These signatures can be chemical, physical, or biological markers that suggest the presence of living organisms. Identifying biosignatures is essential for determining whether a planet or moon has the potential to support life, making them a primary focus in the search for extraterrestrial existence. To detect biosignatures on exoplanets, scientists employ various methods, including spectroscopy, which analyzes the light spectrum from a planet's atmosphere. By examining the absorption lines in this spectrum, researchers can identify gases like oxygen, methane, and carbon dioxide, which may indicate biological processes. Additionally, missions like the James Webb Space Telescope are designed to study the atmospheres of exoplanets in detail, searching for these telltale signs. In our own solar system, potential biosignatures have been found on Mars, where methane spikes suggest microbial activity, and on the icy moons of Europa and Enceladus, where plumes of water vapor may harbor organic compounds. Beyond our solar system, the discovery of oxygen and methane in the atmospheres of exoplanets like K218b raises exciting possibilities for finding life beyond Earth. Each biosignature detected brings us closer to understanding the potential for life in the universe. The role of technology. Technology plays a pivotal role in advancing the search for extraterrestrial life, enabling scientists to explore the cosmos like never before. One of the most significant advancements is the James Webb Space Telescope, JWST, which launched in late 2021. With its powerful infrared capabilities, JWST can observe distant exoplanets and analyze their atmospheres for potential biosignatures. This telescope allows researchers to study the chemical composition of exoplanet atmospheres in unprecedented detail, opening new avenues for understanding habitability. In addition to advanced telescopes, artificial intelligence, AI, and data analysis techniques are revolutionizing exoplanet research. AI algorithms can sift through vast amounts of data collected from missions like Kepler and TESS, identifying patterns and potential exoplanets more efficiently than traditional methods. Machine learning models can also predict the likelihood of habitability based on various planetary characteristics, streamlining the search for life-supporting worlds. These technological advancements are enabling deeper exploration of the universe, allowing us to probe regions previously thought unreachable. As we develop more sophisticated instruments and analytical tools, our understanding of the cosmos expands, bringing us closer to answering the age-old question of whether we are alone in the universe. Each technological leap enhances our ability to uncover the mysteries of life beyond Earth. Future missions and goals. The quest to discover extraterrestrial life is set to advance significantly, with several upcoming missions designed to explore our solar system and beyond. One of the most anticipated missions is the Europa Clipper, scheduled for launch in the 2020s. This mission aims to investigate Jupiter's icy moon, Europa, which is believed to harbor a subsurface ocean beneath its frozen crust. The Europa Clipper will conduct detailed reconnaissance of the moon's ice shell and subsurface ocean, searching for signs of habitability and potential biosignatures. In addition to missions targeting distant moons, the Artemis program is focused on exploring the Moon and Mars. With the goal of returning humans to the lunar surface by the mid-2020s, Artemis aims to establish a sustainable presence on the Moon, which will serve as a stepping stone for future Mars missions. By studying the Moon's resources and environment, scientists hope to gain insights that will aid in the exploration of Mars and the search for life on the Red Planet. International collaboration is crucial in these endeavors, as space exploration often requires shared resources, expertise, and funding. Collaborative missions can enhance scientific output and foster peaceful relations among nations, ultimately enriching our understanding of the universe and our place within it. Together, these missions and partnerships pave the way for groundbreaking discoveries in the search for extraterrestrial life. The Big Bang and the expansion of the universe. Welcome to our exploration of one of the most fascinating topics in cosmology, the Big Bang and the expansion of the universe. Imagine a time when everything we know, space, time, matter, and energy, was condensed into an incredibly hot and dense point. This moment, known as the Big Bang, marks the beginning of our universe approximately 13.8 billion years ago. It's not just a theory, it's a cornerstone of modern cosmology that helps us understand how the universe evolved from that singularity into the vast cosmos we see today. In this video, we'll dive into the significance of the Big Bang theory and why it's crucial for understanding the universe's origins. We'll discuss how this monumental event set the stage for the formation of galaxies, stars, and planets, and how it continues to influence the universe's expansion. But that's not all. We'll also explore the evidence that supports this theory, including cosmic microwave background radiation and the redshift of distant galaxies. By the end of our journey, you'll have a clearer picture of how the universe has been expanding ever since that explosive beginning, and what that means for its future. So, if you've ever looked up at the night sky and wondered about the origins of everything around you, you're in the right place. Get ready to spark your curiosity and expand your understanding of the universe as we unravel the mysteries of the Big Bang and its ongoing expansion. The Big Bang Theory explained. At the heart of the Big Bang Theory lies the concept of the initial singularity, a point where all matter and energy were concentrated in an infinitely small and dense state. This singularity is thought to have existed before the universe began to expand. Approximately 13.8 billion years ago, this singularity underwent a rapid expansion, often referred to as cosmic inflation. During this brief moment, the universe grew exponentially, cooling down and allowing particles to form. This expansion continues today, shaping the universe as we know it. One of the most compelling pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, CMB. This faint glow, detected in every direction of the universe, is a remnant of the heat from the early universe, providing a snapshot of the cosmos just 380,000 years after the Big Bang. The CMB serves as a crucial piece of evidence, confirming predictions made by the Big Bang model and offering insights into the universe's structure and composition. Key figures have played pivotal roles in the development of the Big Bang Theory. One such figure is Belgian priest and physicist Georges Lemaitre, who first proposed the idea of an expanding universe in the 1920s. His groundbreaking work laid the foundation for what would later become the Big Bang Theory, influencing other scientists like Edwin Hubble, who provided observational evidence of this expansion. In this section, we've explored the fundamental concepts of the Big Bang Theory, from the initial singularity to the evidence that supports it, and the brilliant minds behind its development. Understanding these concepts is essential for grasping the origins of our universe. Cosmic inflation. Cosmic inflation is a theory that describes a period of extremely rapid expansion of the universe that occurred just after the Big Bang. This brief but intense phase of expansion, lasting only a fraction of a second, is significant because it helps to explain why the universe appears so uniform and isotropic on large scales. During inflation, regions of space that are now far apart were once in close contact, allowing for the smoothing out of temperature fluctuations and density variations. One of the key issues that inflation addresses is the horizon problem. This problem arises from the observation that distant regions of the universe have nearly the same temperature, despite being too far apart to have ever exchanged information or energy. Inflation provides a solution by suggesting that these regions were once close together before being rapidly stretched apart, allowing them to reach thermal equilibrium before inflation took over. The timeline of inflation is crucial to understanding its impact on the observable universe. It is believed to have occurred within the first 10 to the power of -36 to 10 to the power of -32 seconds after the Big Bang, expanding the universe by a factor of at least 10 to the power of 26 times in a tiny fraction of a second. This rapid expansion not only smoothed out the universe, but also set the stage for the formation of structures like galaxies and clusters. In summary, cosmic inflation plays a vital role in our understanding of the universe's expansion. By addressing key cosmological problems and shaping the observable universe, it provides a framework for comprehending the vast and intricate cosmos we inhabit today. Evidence of expansion. The expansion of the universe is one of the most significant discoveries in modern cosmology, and much of the evidence supporting this idea comes from the groundbreaking work of astronomer Edwin Hubble. In the 1920s, Hubble observed that distant galaxies were emitting light that appeared red-shifted, meaning their light waves were stretched to longer wavelengths. This redshift is a crucial indicator that these galaxies are moving away from us, suggesting that the universe itself is expanding. The redshift phenomenon occurs due to the Doppler effect, which is the same principle that causes the sound of a passing siren to change pitch. When an object moves away from an observer, the wavelengths of its emitted light are stretched, resulting in a shift toward the red end of the spectrum. Hubble's observations revealed a direct correlation between the distance of galaxies and their redshift, leading to the formulation of Hubble's law. This law states that the farther away a galaxy is, the faster it appears to be receding from us, providing strong evidence for an expanding universe. The implications of this expansion are profound and raise important questions about the fate of the universe. If the universe continues to expand indefinitely, it could lead to a scenario known as the Big Freeze, where galaxies drift apart and stars eventually burn out. Alternatively, if the expansion slows down and reverses, it could result in a Big Crunch, where the universe collapses back into a singularity. Understanding the expansion of the universe not only sheds light on its origins, but also helps us contemplate its ultimate destiny. Dark energy and the accelerating universe. Dark energy is one of the most enigmatic components of our universe, accounting for approximately 68% of its total energy content. Despite its significant presence, dark energy remains poorly understood, making it a central mystery in modern cosmology. It is defined as a form of energy that permeates all of space and exerts a negative pressure, which is thought to be responsible for the accelerated expansion of the universe. The discovery of the universe's accelerating expansion in the late 1990s was a groundbreaking moment in cosmology. Observations of distant supernovae revealed that not only is the universe expanding, but the rate of that expansion is increasing over time. This unexpected acceleration can be attributed to dark energy, which counteracts the gravitational forces that would otherwise slow down the expansion. Essentially, dark energy acts as a repulsive force, pushing galaxies apart and driving the universe's expansion to accelerate. Current research into dark energy is vibrant and multifaceted, with scientists exploring various theories to explain its nature. One prominent theory is the cosmological constant, originally proposed by Albert Einstein, which suggests that dark energy is a constant energy density filling space homogeneously. Other theories include dynamic models, where dark energy changes over time, and modifications to general relativity itself. As researchers continue to investigate dark energy, they employ advanced observational techniques, such as studying the cosmic microwave background radiation and large-scale structure of the universe. Understanding dark energy is crucial, not only for grasping the universe's expansion, but also for unraveling the fundamental laws that govern our cosmos. The future of the universe. As we gaze into the cosmos, one of the most intriguing questions we face is, what will happen to the universe in the future? Based on our current understanding of cosmology, several potential scenarios emerge regarding the universe's fate. Two of the most discussed outcomes are the Big Freeze and the Big Crunch. The Big Freeze, also known as heat death, suggests that the universe will continue to expand indefinitely. As galaxies drift apart and stars exhaust their nuclear fuel, the universe will grow colder and darker. Over trillions of years, stars will die, and matter will become increasingly sparse. Eventually, the universe may reach a state of maximum entropy, where no thermodynamic free energy exists to sustain processes that increase entropy. In this scenario, the universe would become a vast, empty expanse, devoid of light and life. On the other hand, the Big Crunch posits that the expansion of the universe could eventually slow down and reverse, leading to a collapse back into a singularity. This scenario would result in all matter and energy being compressed into an infinitely dense state, potentially leading to another Big Bang. These concepts not only highlight the potential paths of cosmic evolution, but also encourage us to reflect on humanity's place in this vast universe. As we ponder our existence amidst the grandeur of the cosmos, we are reminded of the fleeting nature of life and the importance of understanding our universe. Whether we face a big freeze or a big crunch, the journey of exploration and discovery continues, inviting us to seek knowledge about the universe and our role within it. The formation of the first galaxies and dark matter. Welcome to our exploration of one of the most fascinating chapters in the story of the universe, the formation of the first galaxies and the crucial role dark matter played in this cosmic drama. In this video, we'll take you on a journey back in time, to the moments just after the Big Bang, when the universe was a hot, dense soup of particles. We'll discuss how, against this backdrop, the first galaxies began to take shape, paving the way for the rich tapestry of stars and planets we see today. But what exactly is dark matter, and why is it so important? You might be surprised to learn that while we can't see dark matter directly, it makes up about 27% of the universe's total mass and energy. It's the invisible glue that holds galaxies together, influencing their formation and evolution. Throughout this video, we'll break down complex concepts into digestible pieces, making it easy for you to grasp how dark matter interacts with visible matter to create the stunning structures we observe in the cosmos. So, whether you're a seasoned astrophysics enthusiast or just curious about the universe's early days, stick around. We promise to make this journey engaging and informative, sparking your curiosity about the origins of galaxies and the mysterious forces that shaped them. Let's dive in. The Big Bang and cosmic evolution. The Big Bang theory is the leading explanation for the origin of our universe, describing how it began as an incredibly hot and dense point approximately 13.8 billion years ago. In an instant, this singularity expanded rapidly, marking the birth of space and time. The initial conditions of the universe were extreme, with temperatures soaring to trillions of degrees, creating a chaotic environment filled with fundamental particles like quarks and electrons. As the universe expanded, it began to cool, allowing these particles to combine and form protons and neutrons. This cooling process set the stage for cosmic evolution. Within just a few minutes after the Big Bang, nuclear fusion occurred, leading to the formation of the first light elements, hydrogen, helium, and trace amounts of lithium. However, it wasn't until about 380,000 years later, when the universe cooled enough for electrons to combine with protons, that neutral atoms formed, allowing light to travel freely. This event is known as the recombination era and marks the release of the cosmic microwave background radiation we observe today. Key concepts like cosmic inflation also play a crucial role in our understanding of the universe's evolution. This rapid expansion, occurring just fractions of a second after the Big Bang, smoothed out irregularities and set the stage for the formation of galaxies. Temperature fluctuations in the early universe created density variations, which eventually led to the gravitational collapse of matter, forming the first galaxies. Understanding these processes helps us appreciate the intricate history of our universe. What are galaxies? Galaxies are vast systems that consist of stars, gas, dust, and dark matter, all bound together by gravity. They are the fundamental building blocks of the universe, playing a crucial role in its structure and evolution. Understanding galaxies helps us comprehend the larger cosmic landscape, as they serve as the homes for billions of stars and potentially countless planets. There are three primary types of galaxies: spiral, elliptical, and irregular. Spiral galaxies, like our Milky Way, feature a flat, rotating disk with arms that spiral outward, filled with stars and nebulae. Elliptical galaxies, on the other hand, have a more rounded shape and lack the distinct structure of spiral arms, often containing older stars and less gas and dust. Irregular galaxies do not fit neatly into these categories. They have chaotic shapes and are often rich in star-forming regions. Galaxies are not static. They evolve over time through processes such as mergers and interactions with other galaxies. They form from clouds of gas and dust that collapse under their own gravity, often influenced by dark matter, which provides the necessary gravitational pull. As these materials come together, they ignite nuclear fusion in stars, leading to the birth of new stellar systems. This dynamic interplay of forces and materials not only shapes individual galaxies, but also contributes to the overall evolution of the universe, making them essential to our understanding of cosmic history. The role of dark matter. Dark matter is a mysterious and invisible substance that makes up about 27% of the universe's total mass and energy. Unlike ordinary matter, which forms stars, planets, and living beings, dark matter does not emit, absorb, or reflect light, making it undetectable by conventional means. Its presence is inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the most significant influences of dark matter is its role in galaxy formation. As the universe expanded and cooled after the Big Bang, regions of higher density began to form. Dark matter, with its gravitational pull, acted as a scaffold, attracting ordinary matter and facilitating the clumping together of gas and dust. This gravitational influence allowed galaxies to form and evolve over billions of years, shaping the cosmic landscape we observe today. Current theories and evidence supporting the existence of dark matter include observations of galaxy rotation curves, which show that stars at the edges of galaxies move faster than expected based on visible mass alone. Additionally, gravitational lensing, where light from distant objects is bent by the gravitational field of dark matter, provides further evidence of its presence. The cosmic microwave background radiation also shows patterns that suggest the influence of dark matter in the early universe. While dark matter remains elusive, ongoing research continues to deepen our understanding of its critical role in the formation and evolution of galaxies. Formation of the first galaxies. The formation of the first galaxies marks a pivotal moment in the history of the universe, occurring within a few 100 million years after the Big Bang. The conditions necessary for galaxy formation in the early universe were unique. As the universe expanded and cooled, regions of slightly higher density began to emerge, creating the seeds for future galaxies. These regions were primarily composed of hydrogen and helium, the lightest elements formed during the Big Bang. Gas clouds played a crucial role in the formation of these early galaxies. As gravity pulled these clouds together, they began to collapse under their own weight. This gravitational collapse led to the formation of dense cores within the clouds, where temperatures and pressures rose sufficiently to ignite nuclear fusion, giving birth to the first stars. These stars were massive and short-lived, and their intense radiation and stellar winds had a profound impact on their surroundings. The significance of the first stars cannot be overstated. They not only illuminated the dark universe, but also enriched the surrounding gas with heavier elements through supernova explosions at the end of their life cycles. This process, known as cosmic reionization, helped to shape the evolution of galaxies by providing the necessary materials for subsequent generations of stars and planets. The interplay between gas clouds, gravitational forces, and the first stars laid the foundation for the complex structures we observe in the universe today, marking the beginning of galaxy formation and evolution. Observational evidence. Observing the first galaxies and dark matter presents unique challenges due to their immense distances and faintness. However, advancements in telescope technology and observational methods have significantly enhanced our ability to study these cosmic phenomena. Ground-based telescopes, such as the Very Large Telescope, VLT, in Chile, and space-based observatories like the Hubble Space Telescope, have been instrumental in capturing light from distant galaxies. These telescopes utilize advanced imaging techniques and spectrographs to analyze the light emitted from galaxies, allowing astronomers to determine their composition, distance, and movement. Recent studies have led to key discoveries, including the identification of some of the earliest galaxies formed just a few 100 million years after the Big Bang. Observations of these galaxies have provided insights into their structure and star formation rates, revealing how they evolved over time. Additionally, gravitational lensing, an effect caused by the bending of light from distant objects by massive foreground objects, has offered indirect evidence of dark matter, helping to map its distribution in the universe. Simulations also play a crucial role in understanding galaxy formation and the influence of dark matter. By using computational models, astronomers can recreate the conditions of the early universe and study how galaxies formed and evolved over time. These simulations help bridge the gap between theoretical predictions and observational data, providing a comprehensive picture of the processes that shaped the cosmos. Together, these observational methods and simulations continue to deepen our understanding of the universe's earliest structures and the elusive nature of dark matter. Current research and future directions. Ongoing research into galaxies and dark matter is at the forefront of modern astrophysics, with several exciting projects and missions aimed at unraveling the mysteries of the universe. One of the most significant advancements is the James Webb Space Telescope, JWST, launched in late 2021. JWST is designed to observe the universe in infrared wavelengths, allowing it to peer through cosmic dust and capture light from some of the earliest galaxies formed after the Big Bang. Its advanced capabilities promise to provide unprecedented insights into galaxy formation, star formation rates, and the chemical evolution of the universe. Understanding dark matter is crucial for cosmology, as it constitutes a significant portion of the universe's mass and influences the formation and behavior of galaxies. Ongoing research aims to map dark matter's distribution and understand its properties, which could lead to breakthroughs in our understanding of fundamental physics. Projects like the European Space Agency's Euclid mission, set to launch in the near future, will focus on measuring the geometry of the universe and the effects of dark matter on galaxy formation. As researchers continue to gather data from these missions, potential breakthroughs in galaxy formation theories are on the horizon. New findings may challenge existing models and lead to a deeper understanding of how galaxies evolve over time. By combining observational data with theoretical frameworks, scientists hope to refine our understanding of the universe's structure and the role dark matter plays in shaping it, paving the way for future discoveries in cosmology. As we wrap up, we encourage you to subscribe to our channel for more engaging content on astronomy and the wonders of the universe. If you enjoyed this video, please like and share it with fellow space enthusiasts. Don't forget to explore our related videos, where we dive deeper into topics like cosmic evolution, the life cycles of stars, and the mysteries of dark energy. Thank you for joining us on this cosmic journey, and we look forward to exploring more of the universe with you. Asteroid impacts and their role in Earth's history. Asteroid impacts are one of the most fascinating yet often overlooked events in Earth's history. In this video, we will dive deep into the significance of these cosmic collisions and how they have shaped our planet over millions of years, from the dramatic extinction of the dinosaurs to the formation of craters that dot our landscape. Asteroid impacts have played a crucial role in the evolution of life on Earth. We'll start by exploring what asteroids are and where they come from, setting the stage for understanding their potential threat to our planet. Then, we'll take a closer look at some of the most significant impacts in history, including the infamous Chicxulub impact that led to the demise of the dinosaurs around 66 million years ago. This event not only changed the course of life on Earth, but also paved the way for mammals, including humans, to thrive. Throughout the video, we'll engage with stunning visuals and expert insights to illustrate the science behind these impacts. You'll learn about the geological changes they cause, the potential for future impacts, and what scientists are doing to monitor and mitigate these risks. By the end of our journey, you'll have a deeper appreciation for the role of asteroid impacts in shaping our planet's history and the ongoing importance of studying these celestial bodies. So, buckle up as we embark on an exciting exploration of the cosmos and its influence on Earth. What are asteroids? Asteroids are small, rocky bodies that orbit the Sun, primarily found in the vast expanse of space between Mars and Jupiter, known as the asteroid belt. These remnants from the early solar system are believed to be leftover building blocks that never coalesced into planets. Composed mainly of rock and metal, asteroids vary in size, shape, and composition, ranging from a few meters to hundreds of kilometers in diameter. There are several types of asteroids, categorized based on their composition. C-type, or carbonaceous asteroids, are the most common and are rich in carbon. S-type, or silicate asteroids, contain a higher proportion of metals and silicate minerals. Finally, M-type asteroids are metallic and often contain nickel and iron. Each type provides valuable insights into the conditions of the early solar system and the materials that formed the planets. The asteroid belt plays a significant role in our understanding of planetary formation. It acts as a barrier between the inner rocky planets and the outer gas giants, preventing the two from colliding and merging. This region is not only a treasure trove of scientific information, but also a potential resource for future space exploration. It's important to distinguish asteroids from comets and meteoroids. While asteroids are primarily rocky, comets are icy bodies that release gas and dust when they approach the Sun, creating a glowing coma and tail. Meteoroids, on the other hand, are smaller fragments that can originate from asteroids or comets and become meteors when they enter Earth's atmosphere. Understanding these differences enriches our knowledge of the solar system and its dynamic nature. Historical asteroid impacts. Throughout Earth's history, significant asteroid impacts have left indelible marks on our planet, shaping its geological and biological landscape. One of the most famous events is the Chicxulub impact, which occurred around 66 million years ago. This catastrophic collision, caused by a roughly 10-kilometer-wide asteroid, is widely believed to have triggered the mass extinction event that wiped out approximately 75% of all species, including the dinosaurs. The impact created a crater over 150 kilometers in diameter, located on the Yucatan Peninsula in Mexico, and its effects were felt globally, leading to dramatic climate changes. Geological evidence of these impacts can be found in various forms, including impact craters, shocked quartz, and layers of iridium-rich clay. Iridium is rare on Earth but abundant in asteroids, making its presence a telltale sign of an extraterrestrial impact. The study of these geological markers helps scientists piece together the timeline and consequences of past impacts. In addition to the Chicxulub event, other notable impacts include the Tunguska event in 1908, which flattened over 2,000 square kilometers of forest in Siberia, and the Barringer crater in Arizona, formed about 50,000 years ago. Each of these events provides crucial insights into the frequency and scale of asteroid impacts throughout Earth's history. By examining the timeline of these significant impacts, we can better understand the potential threats posed by asteroids today and the importance of monitoring near-Earth objects. The legacy of these historical events continues to influence our planet and serves as a reminder of the dynamic forces at play in our solar system. Effects of asteroid impacts. Asteroid impacts can have profound immediate and long-term effects on Earth, reshaping both the environment and the course of life. When an asteroid strikes, the immediate consequences are often catastrophic. The energy released during an impact can be equivalent to millions of atomic bombs, resulting in massive shock waves, intense heat, and widespread fires. These events can lead to significant environmental changes, including the release of dust and debris into the atmosphere, which can block sunlight and disrupt photosynthesis. This phenomenon, known as impact winter, can drastically lower global temperatures, affecting ecosystems and food chains. In the long term, these environmental changes can lead to mass extinctions. The most notable example is the Chicxulub impact, which is linked to the extinction of the dinosaurs. The drastic climate shifts and habitat destruction caused by the impact created conditions that many species could not survive. Such mass extinctions have occurred multiple times in Earth's history, often following significant asteroid impacts, highlighting the vulnerability of life to cosmic events. Additionally, asteroid impacts can create new geological features that alter the landscape. Impact craters, such as the Barringer crater in Arizona and the Sudbury Basin in Canada, are prime examples of how these collisions can leave lasting marks on the Earth's surface. Over time, these craters can evolve into unique geological formations, influencing local ecosystems and geology. In summary, the effects of asteroid impacts are far-reaching, affecting the environment, leading to mass extinctions, and creating new geological features. Understanding these impacts helps us appreciate the dynamic history of our planet and the ongoing influence of celestial bodies. Asteroids and life on Earth. The relationship between asteroid impacts and the evolution of life on Earth is a complex and intriguing one. While many impacts have led to catastrophic events and mass extinctions, some researchers suggest that certain asteroid collisions may have played a crucial role in the development of life itself. For instance, the delivery of water and organic compounds through asteroid impacts could have provided the essential ingredients for life to emerge in the primordial oceans. This theory posits that asteroids acted as cosmic delivery vehicles, seeding Earth with the building blocks necessary for biological processes. Moreover, significant asteroid impacts have been linked to evolutionary milestones throughout Earth's history. The most famous example is the Chicxulub impact, which not only caused the extinction of the dinosaurs, but also paved the way for mammals to flourish. With the dinosaurs gone, mammals diversified and evolved into the myriad species we see today, including humans. This event illustrates how asteroid impacts can create opportunities for new life forms to emerge and thrive in the aftermath of destruction. Impacts also play a vital role in shaping biodiversity. By altering habitats and creating new ecological niches, asteroid collisions can drive evolutionary change. For example, the formation of impact craters can lead to unique environments that foster the development of specialized species. Over time, these changes contribute to the rich tapestry of life on Earth. In summary, while asteroid impacts are often associated with destruction, they also have the potential to catalyze the evolution of life and shape biodiversity. Understanding this relationship helps us appreciate the intricate connections between cosmic events and the history of life on our planet. Modern-day threats. As we look to the future, concerns regarding asteroid impacts remain a pressing issue for scientists and policymakers alike. The likelihood of future asteroid impacts on Earth is a topic of ongoing research. While large impacts are rare, smaller asteroids enter our atmosphere more frequently, and even a modest-sized asteroid could cause significant damage if it were to strike a populated area. Estimates suggest that there are millions of near-Earth objects, with only a fraction currently being tracked, highlighting the importance of vigilance in planetary defense. To address these concerns, current monitoring and detection efforts have ramped up significantly in recent years. Organizations like NASA's Near-Earth Object Observations Program and the European Space Agency's Space Debris Office are dedicated to identifying and tracking asteroids that could pose a threat to Earth. Advanced telescopes and radar systems are employed to detect these objects, assess their trajectories, and predict potential impacts. Public awareness and international collaboration are also crucial in enhancing these efforts, as many countries contribute to the global monitoring network. In terms of impact prevention or mitigation, several strategies are being explored. One promising approach is the kinetic impactor technique, which involves sending a spacecraft to collide with an asteroid to alter its trajectory. Another method under consideration is the gravitational tractor, where a spacecraft would use its gravitational pull to gently nudge an asteroid off its collision course. Additionally, developing early warning systems and conducting impact simulations can help prepare for potential threats. In summary, while the threat of asteroid impacts is real, ongoing monitoring and innovative strategies for mitigation are essential in safeguarding our planet for future generations. The video explores the significant impact of asteroids on Earth's history, including their role in major extinction events like the one that wiped out the dinosaurs. It highlights how asteroid impacts have shaped geological features and possibly influenced the evolution of life, leading to the emergence of new species. The potential threats posed by near-Earth objects are emphasized, underscoring the importance of planetary defense and monitoring efforts to prepare for future impacts. In another segment, the video discusses galaxy formation, emphasizing the role of dark matter and gravitational forces following the Big Bang. It covers different galaxy types and the advancements in observational technology, such as the James Webb Space Telescope, which may reveal more about early galaxies and dark matter. The concluding section recaps the Big Bang theory, cosmic inflation, and evidence for the universe's expansion, while reflecting on humanity's place within this dynamic cosmos. Viewers are encouraged to engage with the content by subscribing, liking, and sharing to spread awareness and foster a deeper understanding of these cosmic phenomena.